Aloha, this is Roger Brewer with the Hawaii Department of Health. This is a recording of a presentation entitled Evaluation of Environmental Hazards at Sites with Contaminated Soil and Groundwater. Originally gave this presentation November 21st, 2017. This is part 6 of a 6-part webinar series put on by our office. Parts 1 through 5 of the series put on earlier this year discuss the investigation and characterization of contaminated properties. It's appropriate that we spent 5 parts of this 6-part series on the characterization of properties. It's really important that you get proper data before you move on to evaluating the potential environmental hazards posed by contamination identified at the site. So in part 6 of this series now, we'll be moving on and actually looking at environmental hazard evaluation, as our office refers to something often called risk assessment, to identify potential environmental hazards posed by contamination. There are 2 primary guidance documents for the investigation, remediation, and management of contaminated properties published by our office. The first document discusses testing soil, water, and air for contamination. It's referred to as our technical guidance manual. This was discussed in the first 5 parts of this webinar series. The second major document that we publish is referred to as Evaluation of Environmental Hazards at Sites with Contaminated Soil and Groundwater. The same title is used in this presentation. Again, this is used to determine if there is a problem at the site for identifying contamination. There are 2 editions of this document. First, referred to as the Hawaii edition. In this document, we present what we refer to as environmental action levels for soil, water, and air. And the second edition of this document, referred to as the Tropical Pacific edition. In this document, we refer to these same action levels as screening levels or environmental screening levels. The first document, the Hawaii edition, incorporates Hawaii-specific standards. And the second document, the Tropical Pacific edition, refers to non-Hawaii specific standards, usually derived from USEPA or other references, originally developed for use in CNMI and Guam. These webinars will be posted to the webpage you see below. I always like to start off with this quote from Confucius. There are 3 methods to gain knowledge. The first, reflection, is the noblest. The second, imitation, is the easiest. And the third, experience, is the bitterest. I like to think of reflection as research, where maybe we sit in our cubicles and think of new ideas and new approaches to do things. The second, imitation, is essentially guidance, where we're copying what other people have done. And the third is experience, is what we actually experience in the field, where we may determine that approaches done in the past, which has been our case, for example, for discrete samples, don't really work. They're not as reliable as we thought they were. So we have to start over with reflection and finding new paths to achieve our objectives. I like to break site investigations into 3 separate processes. First, site characterization, again, where we go out to the field to characterize a site. We collect samples of soil, water, and or air to identify potential contamination problems. The second part of the process we refer to as environmental hazard evaluation. You could also think of this as risk assessment, although that tends to be a more restricted term. So under environmental hazard evaluation, we review the data from the field and then determine if there's a potential problem at the site. If there is, then we move on to response action. This may include remediation of the site, long-term management, or if we determine there's not a problem, then the response is no further actions needed. And one of the big problems we've had in the last 30 years in the United States was it would take years and years to complete a project, to investigate and clean up a site. I often hear from other colleagues of mine that it takes years to do this process, to investigate and clean up a site. If you actually look at the response action, the remediation, that usually only takes a few months. Most of the time is spent characterizing the site and determining if there is a problem. So we spent the last 10 years or more in Hawaii trying to come up with ways to expedite this process. So that the past use of unreliable discrete sample data has been a huge problem in dragging out site investigations. That, and in combination with excessively conservative action or screening levels, it's added years to project completion. This is really one of the main causes of brownfields in the United States. It's not so much a lack of money, it's more a lack of certainty and a clear endpoint to a project, especially when you're attempting to characterize a site as one spoonful or one pinch at a time, as the case with discrete samples. Or if you're trying to characterize a site down to unrealistically low screening levels where you get lost in ambient background or anthropogenic background. So as we discussed in the first 5 webinars, the use of systematic planning processes, DU MIS investigation methods ensures the resulting data can be useful for final decision making. So it provides a very clear endpoint to the investigation. You may need to go back and do more work, but it's a very clear step-by-step process. And this significantly expedites site characterization, remediation, and closure, where now, if we could do everything correctly at the beginning, we could get in and easily characterize a site and remediate a site within 12 months, or a much shorter time than that, maybe in just a few months, but definitely not several years as has been the case in the past. So in the first webinar series that we gave beginning last June, in parts 1 and 2, we discussed systematic planning and decision unit designation. This is essentially something we've always done in the past, where you're looking at the site history and deciding what parts of the site need to be tested for potential contamination. We're really focused on decision unit designation, so you designate areas of the site for testing. So for example, in the photograph on the right, you see the brown surface soil fill material here. We might test it to see if there's any current exposure to people walking around on this site. This happens to be a park, or any direct exposure concerns. We also may designate deeper decision units. Here you see the white coralline fill material. Some of this material, not here but in other places, was known to be contaminated with lead. So we may designate separate subsurface decision units to look at potential risks, say, to trench workers during this construction project. Parts 3 and 5 of the webinars discuss decision unit characterization and especially multi-increment sampling methods. And we start off focusing on problems with discrete samples. We've published a paper earlier this year called A Critical Review of Discrete Soil Sample Reliability. Parts 1 of this paper discuss field study results, where we went to 3 separate sites and collected hundreds of discrete samples side by side, or combinations of sets of discrete samples from the same area, and tested them, and just demonstrated how variable the concentrations of contaminants at each site could be. And this would be completely unknown if you didn't collect replicate samples, which is usually the case. Part 2, we discuss the implications for problems with discrete samples. So we have a separate webinar, or several separate webinars, that discuss our field study and also the basic parts of decision unit MIS investigation methods. So also as part of webinars 3 and 5, we discuss sampling theory and incorporating decision unit methods with multi-increment sampling solutions, where a single sample is collected from multiple points within a targeted area in order to provide representative data for that targeted area, and replicate samples are collected from the same area to test the precision of the data. We also emphasize the need to carry this process through to the laboratory, or when the laboratory receives a multi-increment sample, which typically they'll weigh 1 to 2 kilograms, and there's a lot of theory behind this, then they have to process it very carefully and also test it very carefully with minimum masses required. One point we tried to emphasize in earlier webinars is multi-increment samples are not composite samples. And I know some of my colleagues like to use this term composite. It's more of a field term used in the past by geologists without me, but it's very erroneous with respect to sampling error and the true meaning of composite samples used by farmers and especially miners, people who do mineral exploration. So a composite of discrete samples example is shown in the upper photograph here, and the true meaning of a composite sample is where a sample collected in different areas of a site, which you expect to be contaminated at different levels, are combined in the field or in the laboratory for testing as a single composite sample. So you're compositing decision units. So this was done in the past in order to save money on analytical costs, because people were collecting lots of discrete samples to characterize a site, sometimes in quite a vain attempt. When you get your results back from the laboratory, you have to multiply the results by the number of decision units represented by those samples. And of course, in this case, 1 sample per decision unit. It's the same thing as multiplying by the number of samples collected, but it's really emphasized the number of decision units. And what this was intended to do is demonstrate that the concentration of contaminant within any one of those areas, assuming 3 out of the 4 in this example were clean, would be 4 times as high as what was reported by the laboratory. Now, you could do the same process with multi-increment samples. Let's say we have the same 4 decision units, and these example decision units I'm showing here, they're kind of small. They could be really huge. They could be an acre in size or half acre or something. But in this case, we're still collecting a single sample once again from each decision unit, but now we're collecting that single sample from lots of points, 30 to 50 or 75 points within each area. And we're collecting a really large sample, not just a small random 4-ounce jar. So again, for each one of the decision units, we have a single sample. Now, if we wanted to, we could combine these all into one huge sample and have the laboratory just test it once as a single sample. But then again, we multiply the results by the number of samples or the number of decision units represented by that composited sample, and that gives us the worst case scenario for the concentration of the contaminant within any one DU. We would never do this in the field. Once you spent this much time collecting these samples, it would be really stupid, to be honest, to composite these. So multi-increment samples are not composite samples, and it's a bad idea, not allowed under our guidance, to composite multi-increment samples. That's a key point. The term composite has very strict meanings under some past regulatory documents, especially with TSCA and PCBs. Part 4 of the webinar, John Peard came in again to finish the first part and just went over details of the field implementation of decision unit MIS investigation methods. So in Hawaii, we've tested well over 1,000 sites now using DU MIS investigation methods. So John emphasized some of the lessons learned in the field. Again, these are posted to our web page. So now we have the field part down. What we want to do today is discuss environmental hazard evaluation, or how we evaluate the data now that we finally have a process to collect reliable, reproducible, and scientifically based data. We've already discussed site characterization process. And next we'll move on to an overview of potential environmental hazards, discuss what the potential problems are we should be looking for in the field. Then we'll discuss how environmental action levels or environmental screening levels are developed to screen for these potential problems in the field once we have our data. Also do a quick comparison to the USEPA regional screening levels and other screening levels, just discuss similarities and differences between our guidance and their guidance. And we'll give some examples of initial identification of potential environmental hazards, and we'll also advance the evaluation of environmental hazards. Once you've identified a potential problem, it doesn't mean there's a potential problem. There is a real problem at the site. It just means you need to look at that in more detail. Now we'll discuss real quickly how an environmental hazard evaluation report should be put together, the information should be included, and we'll discuss environmental hazard management plans, again very briefly, or how to manage contamination identified at the site long term if it can't be remediated. And we're going to end up discussing issues of risk versus remediation and how screening levels or action levels are usually designated or developed based on a more conservative risk than the risk that we would actually use to require remediation at a site. This is a very key part or key point for risk assessors and also for people involved in remediation and making decisions if a site needs to be remediated. So first, the basics of environmental hazard evaluation. So multiple fields of expertise are required to do this. And again, you could think of this as risk assessment, but really what we refer to as environmental hazard evaluation goes beyond what's traditionally thought of as risk assessment, where it's just focused on toxicology. So under our program, then everyone is involved initially to determine what the DUs are at a site or how to designate areas for investigation. You need to get the risk assessors involved, you need to get the remediation experts involved, and you need to get the field people involved who are going to be doing the actual sampling, just to ensure that the data you collect are representative and useful for the decisions you need to make. The chemistry tells us what's there, the geologists could tell us where it is, physics tell us where it's going, toxicologists can tell us what it can do to us, and in combination this can tell us what the concerns are at the site. I always like to add in the attorneys that they're in, tell us who's going to pay. And so once we have identified these problems and set up the funding to clean it up, then the engineers come in and do the remediation. Of course, in reality, these days it's not really separate between scientists and engineers in these different fields. Most people have multiple fields of expertise themselves just based on their experience. So all this information is directly incorporated into the EHE guidance and into the EALs, again, just to compile this information and expedite the process of identifying potential problems at a site. I think I forgot to mention in the past, we did a study in the early 1990s when Hawaii was first developing their guidance. just determine how long it was taking to clean up these sites and what the problems were. At that time, it was taking an average of 1 year to 1.5 years just to complete a risk assessment, or just to identify problems at a site once you already have the data in place. So these screening levels we started developing back then, or action levels as we decided to call them, expedite that process tremendously. What took us a year and a half in the past, we can just do in a few minutes now by incorporating all this information you see in front of us, all this expertise. Let's review the potential environmental concerns associated with contaminated groundwater. And these are the key ones that we want to look for at every site as a default. There could be others. So for contaminated soil, what comes to mind first for most people is direct exposure. You see the kid playing in the dark stain on the ground, or construction workers digging in the soil. So direct exposure just means incidental ingestion of soil, from licking your fingers during lunch, or breathing vapors emitted from the soil, or dermal contact with contaminated soil and the contaminants absorbing through your skin. This applies to humans. We usually just refer to that as direct exposure. Ecotoxicity is the same issue. It's just more for bugs and bunnies, or ecoreceptors at a site if there's a sensitive environmental habitat that's been impacted. A big issue with contaminated soil in Hawaii, and really it should be in most places, is leaching of contaminants from the soil and contamination of underlying groundwater. Also, if their soil is contaminated with volatile chemicals, there could be problems with vapor intrusion, where vapors, instead of being emitted to outdoor air, are pulled into under-pressured buildings overlying the contamination. We have separate presentations on this issue. Another common problem with petroleum contamination, really all types of contamination, but especially petroleum, is what we refer to as gross contamination. In this case, this refers to short-term emissions of vapors from soil, say during construction work, or the presence of sheens, free product that could severely hamper redevelopment projects. Issues like this, just what we typically consider gross contamination in the field. We'll talk about this later, but it's really critical to identify these types of problems ahead of time before redevelopment starts. So those are some of the main concerns with contaminated soil: direct exposure, or ecotoxicity, leaching of contaminants from soil, vapor intrusion in the building, gross contamination. Other potential problems more on a site-by-site basis could include things like uptake of contaminants into produce. That's really a more site-specific call. For contaminated groundwater, it's a similar series of potential environmental concerns. First thing most people think of is impacts to drinking water wells. This could be from a toxicity standpoint. It's more or less direct exposure to contaminated groundwater. Now, if this groundwater is contaminated with volatile chemicals, you could have problems with vapor intrusion. Again, the volatile chemicals coming out of the groundwater intruding into overlying buildings and impacting indoor air if that building is under pressure. We'll discuss this a little bit more later. Also a big issue in Hawaii and in any area that's shoreline areas or areas that are adjacent to rivers or streams is discharges of contaminated groundwater into aquatic habitats and potential impacts to aquatic life. Also, the aquatic habitats could be a source of drinking water, so you have impacts to potential drinking water also. And the last potential environmental concern with contaminated groundwater, again, especially for petroleum type products, it's just gross contamination, free product on top of groundwater that could cause problems during construction work or sudden emissions of really high concentrations of vapors for construction workers, or migration of these vapors into utility lines. These types of problems in the field. It's just a summary of the same environmental hazards we just discussed. So for contaminated soil, you see in pink, I highlighted the human health concerns for direct exposure to contaminated soil or vapor intrusion overlying buildings. If the soil is contaminated with volatile chemicals, you could have leaching of contaminants from soil, gross contamination again, especially for petroleum, and impacts to terrestrial habitats, ecotoxicity. Again, a similar set of potential environmental concerns for groundwater from the human health side, impacts to drinking water resources from a toxicity standpoint, and again, if it's contaminated with volatile chemicals, emission of vapors from contaminated groundwater usually needs to be fairly shallow in intrusion to overlying buildings. Also, gross contamination issues for contaminated groundwater. If it's a source of drinking water, this could be taste and odor concerns in addition to toxicity. That actually drives risk for a lot of petroleum-based chemicals that aren't necessarily that toxic, like xylenes or paint thinner. And lastly, again, discharge of contaminated groundwater into aquatic habitats. So now we have a good set of environmental hazards that should normally be reviewed during a traditional environmental risk assessment. In Hawaii, one other thing we do is we split the groundwater into 4 different zones based on whether groundwater is a source of drinking water and how close it is to an aquatic habitat. So if you see in the upper left-hand corner, zone A1 is intended to represent groundwater that's a source of drinking water, but it's not really close to an aquatic habitat. We use 150 meters as a buffer zone or a separation distance between aquatic habitats to determine whether or not it's considered to be close or not. Now in zone 1, if you look at the chart in the upper right, it's a potential source of drinking water, but it's not very close to an aquatic habitat. So we would screen that groundwater in particular from a toxicity standpoint with respect to drinking water action levels, but also action levels for acute toxicity to aquatic organisms. We don't necessarily have to define the entire extent of the plume to evaluate concerns for potential discharge to aquatic habitats, but we definitely want to outline the areas of the plume that are acutely toxic. And this is important in case of there's some construction in this area and dewatering takes place, say the water is discharged into a storm drain or something. Zone A2, same thing, it's a source of drinking water, but now we're getting very close or even adjacent to an aquatic habitat. In this case, again, we'll screen the groundwater with respect to drinking water action levels or for drinking water concerns. And we'll also want to identify if the groundwater is impacted above chronic aquatic toxicity standards, just to be additionally careful of impacts to discharges or impacts to aquatic habitats. Now in the bottom part of this figure, the groundwater is not a source of drinking water. Zone B1, and this is actually one of the most common zones that we work in Hawaii. It's in the coastal areas. The shallow groundwater is not a source of drinking water, and it's not really close to an aquatic habitat. So in this case, we don't need to screen the groundwater in this area with respect to drinking water action levels or to assess potential drinking water impact concerns. And we're not as concerned about discharges into aquatic habitats. So our primary thing we're looking at with respect to toxicity, eco or human health, is acute toxicity to aquatic organisms. So the screening levels in zone B1, if you selected this scenario during your assessment process, would primarily focus on acute aquatic toxicity with respect to toxicity concerns. Zone B2 we're more concerned about, still not a source of drinking water, but we're adjacent to an aquatic habitat or in close proximity. Zone B2 is not a source of drinking water, but we want to screen the water and identify any areas of groundwater that exceed chronic aquatic toxicity action levels. So now we have the different categories of concerns. We have different environmental concerns to focus on for initial screening, and we've split the groundwater up into 4 different categories to get a better handle on the potential issues associated with different areas of the islands, whether it's a drinking water source or not, and how close it is to an aquatic habitat. Next step is to start compiling references and screening levels for individual environmental concerns. So first here I've highlighted environmental concerns associated with human health. In most cases, we're referring to guidance published by the USEPA. You can see for direct exposure for contaminated soil, we refer initially to the USEPA regional screening levels. We use them as a default, although we'll discuss later on, and we modify their screening levels as appropriate based on background and target risk concerns and such. For vapor intrusion, for groundwater and soil, we refer to USEPA's models. Again, modified for use in Hawaii, and as I'll mention later, modified with respect to our field experience over the last 10 years. Indoor air, we use the EPA's model for ambient air screening levels. For groundwater, we discussed vapor intrusion, we use the US EPA model. For drinking water toxicity, we refer to the Hawaii maximum contaminant level if it's available. If not, then we refer to US EPA's to their regional screening level for tap water. That's human health. For ecotoxicity, for terrestrial habitats, we don't publish action levels or screening levels for contaminants in soil that could pose ecotoxicity concerns. This really has to be a site-by-site assessment depending on the flora and fauna present. For groundwater, however, we screen the groundwater against Hawaii aquatic water quality criteria. These are promulgated water quality standards to protect aquatic habitats if they're published. They're both acute and chronic. If those aren't available, then we refer to other guidance usually compiled by USEPA or other agencies. So we're just going through each one of these environmental concerns. We're essentially compiling action levels for each concern, for each chemical under each one different scenario. Leaching model for soil refers to Massachusetts Department of Environmental Protection. This model was actually developed by Washington State or Oregon in the early 1990s, adopted and modified some by Massachusetts, also used by Wisconsin, several other states, and Ontario. And we'll discuss it later very quickly. It's just a model that you input your target groundwater concentration, the model back calculates a safe concentration in soil to ensure the groundwater isn't impacted above that level. Nuisance concerns, gross contamination concerns, we follow a process published by Massachusetts. Again, this is in the early 1990s, and we'll discuss this later. But gross contamination concerns are again based on short-term vapor emissions of its volatile chemicals and odor thresholds, solubilities, and such. For groundwater, for nuisance concerns, gross contamination, we refer to the secondary MCL for the contaminant, whether it's benzene or xylenes or whatever, if it's promulgated. The secondary MCL focuses on nuisance concerns. If not, then Massachusetts and several other agencies have published screening levels, action levels for taste and odor thresholds for chemicals in groundwater. So here's an example then. We just went through all the sources for each environmental concern. Here's an example of PCE for residential exposed soils over drinking water. And in this case, the site is adjacent to a surface water body. So you see lots of different numbers now we've inserted into each one of the potential environmental concerns. I'm not going to go through each one of these, but now we have a screening level for each concern. If we went out to the site and collected environmental data, soil samples and groundwater samples, we can compare the results to these screening levels for each concern and very quickly identify if there's a potential concern at the site and what that specific concern is. Now this can be kind of complicated, so what we've done in what we refer to as our EAL surfer, is just electronic lookup tables. Our main guidance also is we reduce this down to a single number. So for soil and groundwater, we take the lowest action level for all of the potential environmental concerns, and this becomes our tier 1 action level. If you collect a sample and the data are below this lowest action level for all the concerns, then you're done. All the other concerns aren't going to be an issue either. So for soil, you see the lowest action level for PCE residential soils over drinking water is 0.098 milligrams per kilogram. This just happens to address vapor intrusion to indoor air. So that's our final action level for PCE under this scenario. For drinking water, the final action level is 5 micrograms per liter based on the drinking water MCL for PCE. So in this case, for drinking water, toxicity drives potential risk for PCE contaminated groundwater. This isn't always the case. For less toxic compounds, gross contamination might drive the risk. Like for xylenes, the gross contamination action level is 10 times below the toxicity level. So you can taste it well before you can hits a toxicity level of concern. In other cases like pesticides, the action level for aquatic habitats is far lower than the drinking water action level. This is because the chemical is more toxic to aquatic life than it is to humans. So that's in general the big picture on how the action levels are compiled. We define the specific concerns for soil and groundwater and air that we want to screen for at all sites in general. We look for references for each one of those concerns, and then we take those references and use them either straight up or we modify them for use in Hawaii based on our climate or our specific policies. So we have environmental action levels now for over 150 chemicals. I think over 200 actually. So it's suites of petroleum related chemicals, pesticides, explosives, heavy metals. Volume 1 of the document just presents the tier 1 final EAL. So again, that single number, just give me one number for this chemical under this scenario. Volume 2 goes into the technical background of how the numbers were derived derived, how the action levels are derived, and they give detailed action levels for each individual concern with all the references. Now we've simplified this in an easy-to-use Excel-based, what we refer to as an EAL Surfer electronic lookup table. This was originally developed by a friend of mine, Lawrence Millier. He's with the California EPA. It was a project he did for UC Berkeley back in the early 2000s, which it was huge. It made this whole process much more simple. In this case, I'm not going to go through an example here, but it's on our web page. In one page, you select the site scenario, site use, residential, commercial, industrial, whether groundwater is the source of drinking water or not, and you select your chemical input site data and hit enter, and it immediately identifies potential environmental concerns at your site by comparing your site data to the action levels. So it's great. This allows us to do in really 30 seconds what in the past used to take us a year. Also, it generates summary reports that you can print out and include with your document. One thing that's just happened this year is a state competition to develop apps for your phone or whatever, but we put in a proposal to develop apps for the EAL Surfer to make it even more useful. Those will be coming out hopefully later this year, some beta types, but they allow you to select multiple chemicals at one time, whereas the EAL Surfer is one chemical at a time, and generate a single report for as many chemicals as you want to include in your site investigation document. So the EALs, overall, they allow us to complete a site investigation and to screen out low-risk areas. That's the main issue. So you don't need to investigate a site all the way out to non-detect. We give you a very clear endpoint where the site investigation can be ceased. And also very quickly you can screen out low-risk areas. Hopefully it's your entire site. If not, you can isolate contaminated areas and many times start developing or do whatever you need to with the rest of the site while the remediation is taking place in the area that exceeded environmental action levels or additional evaluations carried out in that area. Let's go through a quick example. In this case, it's a hypothetical former fuel tank farm, and the main contaminants of concern are TPH and BTEX. This is going to look a lot like the Lowe's development on Nimitz Highway in Hawaii. It is based on that, but I compiled ideas from other sites and just tried to simplify it. A key thing to think about here, and we've discussed this quite a bit in the past, is you always collect TPH data at petroleum contaminated sites. We treat TPH exactly like we would any individual compound, benzene, toluene, ethylbenzene, xylenes, or naphthalene, or any other individual compound. This is discussed in detail in our guidance. We published papers on it. At the bottom here is I and Josh Nagashima, Mike Kelly, Mark Rigby, two consultants. Josh and I work together at the Department of Health. We did a field study of the chemistry and toxicity of petroleum vapors and published a paper, Risk-Based Evaluation of Total Petroleum Hydrocarbons and Vapor Intrusion Studies. So we have a very good handle now. We have really for the last 15 years on how to treat TPH as an individual compound, and we have risk-based screening levels for TPH. This isn't that common still in other states, but we've been using it here in Hawaii, and same in California and a few other states, Massachusetts, Oregon, Washington for 10, 20 years. So again, we have toxicity factors and action levels for soil, water, and air available for all potential environmental concerns. TPH often drives exposure risk over BTEX. So refer to some of the webinars that are posted to our webpage. It's a common fallacy we see still in risk assessments, although they're much more rare here in Hawaii, where there's an idea that benzene always drives risk, so we just focus on benzene. I'll show you a photograph later on where a site caught on fire after it passed a risk assessment for benzene because they failed to look at the TPH. But TPH, it's less toxic than benzene, but because there's so much more of it in the soil vapors or even in soil, and maybe even in groundwater, that it drives risk over benzene, but just because it outweighs the mass of contamination present or identified in individual compounds. Another point we make in our guidance is the groundwater metabolites or degradation products of TPH and these other individual compounds. They are assumed to be similar toxicity to the parent hydrocarbons, to the parent TPH. This is discussed in our guidance also. This could be evaluated on a site-specific basis. I and my coworker Iris van der Zander on a nationwide team of TPH risk through ITRC, and we're developing guidance on risk-based approaches to TPH really largely reflects what we've been doing in Hawaii for the last 10 or 15 years, but a new part of this is focusing on metabolites and more general incorporating this information into risk assessments. So remediation or long-term management, again, is often driven by really its gross contamination concerns. The nice thing with TPH, it usually doesn't start posing a toxicity concerns until you can start to see it or smell it or taste it. So it's hard to miss petroleum contamination that pose potential toxicity concerns or environmental concerns in general. So clean up what stinks and smells or tastes bad like we've always been doing, and you're pretty much good to go. So here's an example. This is the former low site. I've made up the maps here. They don't necessarily reflect what happened there. But now that we have these individual action levels for specific concerns, we can actually make what we refer to as an environmental hazard map of a site. And this can be really useful, especially talking with regulators or developers or anyone just designing the remediation project for a site. So you can see here that gross contamination is highlighted in red. This is really the most contaminated parts of this site. In yellow is the area of the contaminated soil and groundwater, I think, included here, that could pose potential vapor intrusion concerns. This is based on soil gas data. You always want to get soil gas data to look at vapor intrusion concerns. Area in blue, again, I'm just kind of making this up, but lower action levels, so it encompasses more of the contamination. This is where the soil exceeds direct exposure action levels, either for future occupants of the site. It's going to be commercial, industrial, or for trench workers. The area of green will sit in between the blue and the yellow. This is the part of the soil that is contaminated to the extent that it could pose leaching problems for underlying groundwater. And then in purple, I just made up an area of groundwater contaminated above aquatic toxicity concerns. So all these come into play then in determining what the remediation strategy for the site. Now, whether or not these individual concerns that they got flagged using these action levels for the site, comparing it to site data, whether or not they pose a problem at the site is something you can look at in a little more detail. So yeah, these are just questions to think about. Are the exposure pathways complete? Maybe the sites can be completely paved over, so there aren't going to be any direct exposure concerns. Although this would obviously imply long-term management issues. So is soil exposed at the site or not? Is leaching really a concern at the site? Our leaching-based screening levels or action levels are highly conservative. We'll discuss that later. If the soil is already in contact with groundwater, just get some groundwater data and see if the groundwater really is impacted above action levels. For vapor intrusion concerns, are there any buildings at the site? If there are no buildings, you're not going to have vapor intrusion issues. Again, it could be a future problem. If the groundwater is flagged for potential discharge to aquatic habitats, where are the aquatic habitats in the area? In this case, there aren't. Definitely nothing within 150 meters. But there are some storm drains going through this site, and the storm drains were in contact with the groundwater. So that's it. So an extra piece you have to think about. Are there any wells impacted at the site? Well, it's not a source of drinking water. And also in this particular site, there's no other wells, or there aren't any other wells for industrial use or irrigation and such. Just things to think about on a site-specific basis. So you might end up doing something like this. It's really typical. This is a former tank farm. It's, I think, a 4 or 5 acre site. Chances are you're just not going to be able to afford to clean up the site to pristine. In this hypothetical example, which is similar to what they did, they took out the area of the site that was contaminated above gross contamination action levels and the area of the site that posed really high risk for vapor intrusion. So that soil was cleaned up, and you're left with residual contamination that can be managed in place. So you took out the high risk contamination, managed the rest in place. So now in case of future buildings being constructed here, and this was the true case here, there's some residual contamination left in place, maybe very minor vapor intrusion problems, but there was concern about methane buildup and degradation over time. So they put a vapor barrier under the entire building. And also you develop a long-term management plan for soil and groundwater, both during the construction phase of the site. Very specific. Here's how you deal with contaminated soil. Here's how you deal with contaminated groundwater. This is referred to an EHMP, Environmental Hazard Management Plan. And then post-construction, maybe some of the soil's been removed or such, you prepare a long-term environmental hazard management plan for the site. So not that complicated if you work through it step by step. So that was just an example. What I want to get into next, or discuss next, is potential environmental hazards in relation to how the chemical partitions in the environment. This really drives the action levels. I'm not going to go into the detailed models here. They're all very similar. I like to think of them as the models used to develop these action levels, like my old 73 Chevy Caprice Classic. It looks pretty complicated at first, but once you look under the hood, the individual parts are pretty simple. It's just put together in a manner that makes it drivable. It's not that difficult to learn the models and such. And again, they're not that complicated. And they have a lot of common parts to them. So in all the models, whether you're looking at direct exposure or vapor emissions or leaching, they all start off with something very similar. Say for contaminated soil, they take the total contaminated soil concentration, or concentration of contaminated soil. They take the total concentration of the chemical in the contaminated soil. And then the models will partition this into a absorb phase, a dissolve phase, or the contaminant that would migrate into the soil moisture, and a vapor phase, the fraction of the contaminant that's going to migrate into vapors. And if there's any extra left over, it would be the free product. And then these are fed into the models for vapor intrusion or soil leaching, or even for direct exposure, or even for gross contamination. Some models can identify the potential presence of NAPL or free product in the soil. Some of the primary chemical specific modeling factors that are used in the model are the Henry's law constant, which is just the ratio of the concentration of the contaminant in vapor phase divided by the concentration of the contaminant in the dissolve phase. So just imagine if you had a glass of water half filled, spiked with PCE, and you sealed it and let it reach equilibrium. What's the ratio of the concentration of the PC in the vapor phase versus the dissolve phase? This is just the Henry's law constant. So they're available for all volatile chemicals. Another very important factor is the sorption coefficient. This is the concentration of the sorb phase contaminant to the dissolve phase contaminant. So if you see in the diagram here, it's where the orange and the blue meet. It's the ratio of the contaminant between the blue, the dissolve phase, and the orange, the sorb phase. There are other physiochemical parameters like solubility, diffusivity constants, and such that are also considered in the models, but they don't necessarily drive the models, drive the results. You have to assume some soil properties to run these models. We assume the same properties used in USEPA regional screening level models. It's semi-moist soil, low organic carbon content, and a few other parameters, high vapor permeability. This is all discussed in Appendix 1 of our guidance document, so I won't go into detail. So here's what happens with the chemicals when they are released to soil, how they partition in the soil. And again, this tends to drive the risk. So imagine benzoate pyrene, if you could release benzoate pyrene to the soil, highly sorptive, not volatile, and not really soluble. So most of the 99.99% of the benzoate pyrene is not free product, is going to sorb to the soil. So when something's tightly bound to the soil, we're not worried about leaching concerns or vapor concerns. The primary concern is eating the soil, a direct exposure, incidental ingestion. Compare that to something like benzene. When we release benzene to the soil, again using this default soil type that's used in EPA's models, the majority of the benzene is going to sorb to organic carbon in the soil. It could even sorb to clay particles. Well, that's not included in the models. Some of it, though, is going to diffuse out and move into the soil moisture and pose potential leaching problems. Some of it's going to go into the vapor phase and pose potential vapor problems. If we're looking at contaminated soil exposed to the surface, even though the smallest fraction of benzene moves into the vapor phase, that's actually the risk driver, because benzene is highly toxic from an inhalation standpoint, and more so than from soil ingestion standpoint. So benzene contaminated soil poses all three problems: incidental ingestion, vapor emissions to outdoor air, as well as vapor emissions to indoor air, and also leaching and impacts to groundwater. Now, something like vinyl chloride or highly volatile chemicals, most of the chemicals are going to move into the vapor phase. So in this case, it's pretty straightforward. Your main risk posed by vinyl chloride contaminated soil is inhalation, whether it's vapors emitted to outdoor air or vapors getting pulled into buildings that overlie the contaminated soil. It would also pose potential leaching problems. You see in blue, some of it's going to move into the dissolve phase, and about a quarter of the vinyl chloride is going to absorb to the soil, where over time it would just slowly desorb from the soil, move into vapor phase, or move into the water phase. So this is just a quick example of different contaminants, different physiochemical properties, and how the physiochemical properties of the contaminant really drive ultimately what the primary risk is posed by that contaminant when it's released to soil. Now we can actually break up different chemical families based on the primary environmental concerns that drive remediation or drive environmental hazards at a site. So leaching concerns are primarily posed by light petroleum, diesel, gasoline, although as we discussed in our guidance in other places they're highly degradable. So this reduces but doesn't eliminate potential leaching concerns. Chlorinated solvents. Think about that. What are the largest plumes we tend to see in contaminated or in groundwater? It's usually PCE, TCE. So these solvents are highly mobile. They're highly volatile. They pose vapor intrusion concerns too, but they're highly mobile. They leach from the soil. They just go straight through the soil and contaminate groundwater. A lot of pesticides, especially used in the past, were they're also highly mobile, so they leach out of the soil and contaminate underlying groundwater. Inorganic salts like perchlorate, not necessarily that toxic in the soil if you were eating pinches of the soil at a time, but their biggest problem is they could leach out of the soil and impact underlying groundwater, impact drinking water resources. That's the risk driver. Direct exposure concerns, again, are posed mainly by contaminants that aren't that mobile. They're not that volatile or leachable. This includes carcinogenic pHs like benzoate pyrene, PCBs, metals like heavy metals like arsenic and lead. Not mobile, main concern, direct exposure, incidental ingestion especially. Vapor emissions, outdoor air, indoor air, that's primarily driven by carcinogenic VOCs, or carcinogenic VOCs primarily pose vapor emission concerns, benzene, chlorinated solvents, PC and TC and such. Terrestrial ecotoxicity, I know we don't have screening levels, but the non-carcinogenic metals like copper, nickel, these types of metals, not that toxic at all to humans, but they can be highly toxic to flora and fauna. And the same thing for a lot of pesticides. They're specifically designed to not be that toxic to humans, but intentionally designed to be toxic to terrestrial flora and fauna. So in these cases, for these chemicals, the primary concern is terrestrial ecotoxicity. Gross contamination concerns, heavy petroleum or even lighter petroleum, diesel, gasoline, petroleum in general. Often need for remediation or primary environmental hazards are driven by gross contamination concerns as much as it is vapor intrusion or leaching or other concerns. And non-carcinogenic metals like a chromium and cadmium and copper, some of these other types of heavy metals, not that toxic, but we have action levels. We can identify when the concentration of, say, chromium in soil is so high that chances are if you went out to the site, you'd see little bits of chromium all over the site. Maybe it's not a problem, maybe it is, but the gross contamination action levels flag this problem, and then you go out to the site, see if it's really an issue. And same thing for solvents like Stoddard solvent or some of the phenols. They're not that toxic, but they can cause odor problems, nuisance problems, or even explosion, fire problems. So that was a summary of the potential environmental concerns in general, and just how fate and transport and the physicochemical parameters for individual compounds ultimately drive potential environmental concerns. So if you give me a compound X, and tell me in general what the toxicity is and what just the Henry's constant, say, is, or the absorption coefficient, the volatility is, then real quickly I can identify, or anyone could identify, what the potential primary environmental hazards posed by that chemical are. So now I want to go through real quickly. I'm not going to go through the models again, but just in general how the action levels are defined or developed for each one of these environmental concerns. So we'll start with direct exposure action levels. This is for water, soil, air. This could be for fruit, anything. They're all derived in the same way. The equations I show below are very simplified. The real equations are a little more complicated, but in general, basically they're fairly easy. They're not that complicated once you look at the individual parts. So the primary thing for direct exposure, again, we're looking at risk. What's the excess cancer risk? What's the non-cancer hazard quotient? And what's the risk posed by this contamination? So risk is a function of your average daily dose. And here we're talking about chronic risk, where exposure to something could be a very, very low concentrations, but exposure over many, many, many years. So risk is a function of the average daily dose, or the mass of this contaminant you're getting in your body every day, times some toxicity factor. And this is usually based on animal studies or other studies, where they develop a toxicity factor. It's not the actual factor or the concentration that's black and white above this. It's toxic. It's just it's really the average daily dose that toxicologists agree doesn't pose a potential health risk. A dose is above this toxicity factor and could pose a potential health risk, but you have to look at it more specifically in more detail. So risk, it's a function of average daily dose times toxicity factor. Average daily dose is a function of the concentration of the chemical in the media, whether it's soil, air, water, or fruit, or whatever, times your exposure rate. Exposure rate is just how much of this media you're being exposed to a day. So default USEPA exposure rates for inhalation, 10 to 20 cubic meters per day, 10 for children, 20 for adults. Soil ingestion, the default EPA exposure rate is 100 milligrams a day for adults, 200 milligrams a day for children. This is for exposure to less than 2 millimeter particles of soil. We'll talk about that later, just incidental ingestion of sand size or flower size particles of soil. Drinking water, the assumption default is 1 to 2 liters of ingestion a day. 1 liter for children, 2 liters for adults. This was recently modified, but it's roughly in those numbers. So that's the average daily dose. So now how do you convert this to an action level? We understand that risk is based essentially on the media concentration times exposure rate times toxicity factor. We can solve this same simple equation for the media concentration, except now this can be our media action level. So the media action level is a function of the target risk divided by the toxicity factor divided by the exposure rate. Now the toxicity risk, target risk, and toxicity factor essentially represent the target maximum average daily dose, where all the toxicologists would agree that this doesn't pose a potential health risk, called a no observed effects level. So your media action level then, or your soil action level, your water action level, your air action level, is this target maximum average daily dose divided by your exposure rate. So let's look at that, just a few examples here. A classic saying by the toxicologist is dose makes the poison. So if someone asks if something is toxic or not, well, everything is toxic at some dose. So water is toxic at a few gallons. If you drink a few gallons of water at once, then you could get acute hyponatremia. I remember a case in California. It was a college hazing event where some guy drank 5 gallons of water, and he died very quickly from acute hyponatremia. Essentially, his cells in his body exploded because he had diluted the fluids flowing through his body so much. So the target risk space, in this case, it's an acute single dose for water, a few gallons. How about for aspirin? Aspirin is more toxic than water. If you look on the bottles of mini-tab aspirins, these tiny aspirin tablets that are intended to take every day, then you'll see they contain 81 milligrams of aspirin. So somewhere there's some detailed toxicity studies that demonstrate that 81 milligrams of aspirin a day taken by an adult, this is roughly equal to, say, 3 drops. He's going to weigh about 81 milligrams, won't pose gastrointestinal tract problems. So if you take these mini-tab aspirin every day and you develop gastrointestinal tract problems, good luck trying to sue the aspirin company, because they have tons of toxicity studies demonstrating that it wasn't the aspirin that caused those problems. How about gasoline, TPH gasoline? Well, gasoline is a little more toxic than aspirin. In this case, the target risk-based average daily dose, which from studies show that this dose is safe for exposure day to day for many years, comes out about 1 drop per month, or in concentration terms or dose terms, 0.9 milligrams per day. That's actually the toxicity factor we use in our action levels to develop our models, direct exposure models, to develop soil action levels. And it's very similar to water and even air action levels, although they can differ a little bit depending on the route of exposure, and multiple problems posed by exposure to gasoline. But you can be exposed to 1 drop of gasoline a month in some form or the other, and it's not going to pose a risk according to these toxicity studies. How about PCBs? They're a lot more toxic than gasoline. For PCBs, the target risk-based average daily dose is 0.0002 2 milligrams per day. Well, how much is that? If you could look at it, that's about a single 1 millimeter diameter grain, say of sand, slowly ingested over 30 years. That's the safe dose for PCBs, which is essentially nothing. So, and PCBs cause multiple chronic health effects. Again, we're looking at chronic health effects over many, many years. These are just general examples, but this is what a toxicologist does. For any chemical, they come up with a toxicity factor, which you look at other factors, including body weight and how many days per year exposed and such. But you essentially develop these risk-based average daily doses. And you see here the examples for a child, assume 15 kilograms chronic exposure over 6 years. And the dose here for PCBs is the non-cancer hazard quotient of equal to 1. So if you were exposed to 0.0002 milligrams per day, that's the risk-based average daily dose, and we say that equals a target hazard quotient, non-cancer concerns of 1. The toxicity factors for the individual chemicals, not only like this, are they very, very low, they also always include at least a 10 or 100-fold safety factor, or almost always. So now we have these average daily doses. How do we develop action levels from these? Well, here's an example for MTBE. The maximum daily dose that the toxicologists agree on from the toxicity factors and such is 28 micrograms per day. Let's assume you drink 2 liters of water per day. Here we're looking at adult exposure over many, many years. So what's the drinking water action level? Well, it's 28 divided by 2. It's 14 micrograms per liter. That's really how simple risk assessment is. It can look really complicated in the strange language they use to prepare risk assessments, but that's all it is. That's how we just do this backwards then to calculate action levels. So here's the example then for PCE direct exposure action levels. We go through the same process for what's my maximum daily exposure. How many cubic meters of air do we inhale a day? 1 to 2, depending on child or adult. This is worked into the model, so the action level comes out to 0.46 micrograms per cubic meter. There are different toxicity factors for inhalation, I should point out, versus, say, ingestion into your stomach. So that the average daily doses or maximum limits don't necessarily equal each other depending on the route. Direct exposure action level for soil, 1.1 milligrams per kilogram. In both these cases, these are based on a 1 in a million risk, and we'll look at that later on, the target risk we use to develop these action levels. So there's our direct exposure action levels for soil. For groundwater, drinking water toxicity, the action level, which is actually a promulgated standard toxicity-based primary MCL, is 5 micrograms per liter. Now in this case, most of the promulgated MCLs for toxicity are based on a 1 in 100,000 excess cancer risk instead of 1 in a million. There are a lot of reasons behind that. For one thing, it's still within a safe range of 10 to the minus 4 to 10 to 1 in a million. So it's accepted as for development of action levels. There's also concerns just about practicality and detection limits and such that are taken into consideration. These are just examples for the soil and air. That we also include separate action levels for commercial industrial exposure. They can be used on a site-specific basis, although they would obviously pose land use restrictions on the property. So I mentioned before that the soil action levels are based on exposure to less than 2 millimeter particles in soil. These are small sand grain sized particles. In our default guidance, where we follow EPA's current default guidance used in the regional screening levels, they assume that a child is ingesting 200 milligrams of these particles per day. So 200 milligrams is, say, 10 or so sand grain sized particles of soil. They assume that the adults ingest 100 milligrams per day. Some risk assessors now are recommending that for direct exposure concerns, we should focus on the really fine fraction, not the coarser particles, because the fine fraction is what children especially are most exposed to. So they're talking about the less than 250 micron fraction or even 150 micron size particles to focus on for incidental ingestion. This is flower-sized particles that tend to stick to your hands. This has a lot of important implications because now we're focusing on the really fine-grained particles. The soil ingestion rate is going to be lower. So the default soil ingestion rate that's proposed along with the exposure to the fine particles for children is 100 milligrams per day instead of 200 milligrams per day. For adults, the equivalent would be cutting that in half, say 50 milligrams per day. The models used to develop these action levels are linear. So if you cut the soil ingestion rate in half, it's going to double the soil action level in both cases. So we already look at testing of less than 250 micron fraction for bioaccessible arsenic, but at the same time we're assuming a 100 milligram per day adult exposure, 200 milligrams per day child soil ingestion rates. Really, this isn't appropriate. We should be cutting these exposure rates in half. We should be looking at 50 to 100 milligrams per day soil ingestion rates for adults and children, but that would involve us doubling the action levels. So again, the problem here is that reducing the ingestion rate by a factor 2 would double the soil direct exposure action levels, since we're ingesting or less soil, we're eating less soil, so a higher concentration is acceptable in the soil. But the concentration of the contaminant in fines, however, it's typically assumed to be double that of the less than 2 millimeter fraction. So you hear us talking about that in our multi-increment sampling webinars and problems with discrete samples. You shake the jar, try to homogenize it. The fines go down to the bottom, and the fines tend to be where most of the contaminants are. So even though we're doubling the action level, if you only tested the fine material, chances are your concentration in the soil is also going to double. So ultimately, there's no net change in the ultimate conclusion based on focusing on the fine soil particles. You're going to double the action levels, but you're going to have twice as high a concentration, so you still have a problem at the site. So for now, we're not going to change our guidance, and really what our guidance assumes, you can think of is that the total soil ingestion rate of 200 milligrams per day, it includes 100 milligrams per day of the really fine particles and 100 milligrams per day of the 150 microns, say, to less than 2 millimeter particles, so the coarser particles. So this would tend to please all the risk assessors. Some risk assessors also want to focus on these coarser grain particles also, because the kids still could get them in their food or on their hands and ingest them. So I know there's a lot of talk currently about reducing the target size fraction that's being tested in the field. Maybe we'll do that on a site-by-site basis. If we do this, we need to adjust the action levels, so just think more about that. So for now, we're not going to change our guidance because it already addresses the fine grain exposure issue. All right, that was a discussion on direct exposure. Let's look real quickly now at vapor intrusion action levels. We use PCE as an example. We have separate webinars on this, and our office has done a lot of field research and a lot of thinking about vapor intrusion. I think we're really well ahead of a lot of the other agencies on the mainland. I think we have a lot more independence to look at these issues and develop guidance. That's another issue that's in the separate webinars. Here's an example of PCE. So let's assume a residential development. Again, here's our indoor air action level, 0.46 micrograms per cubic meter. The next step in a site investigation the first step really is to test the soil vapors immediately underlying the slab of the building. So the action level for soil vapors immediately under the slab of the building, we just multiply, or we divide the indoor air action level by a subslab attenuation factor. In this case, for tropical environments, it's 0.0005, or essentially we multiply the indoor air concentration by 2,000. So this attenuation factor assumes a 2,000-fold attenuation of vapors as they intrude into a building and mix with indoor air, with the indoor air exchange rate, continuously bringing in fresh air. Now we use EPA's vapor intrusion models then to develop action levels for vapor intrusion for soil and for groundwater that we would predict would generate this concentration of PCE in soil gas or soil vapors immediately under the slab, or 920 micrograms per cubic meter. If you run this through the models for soil, it predicts the action level we looked at before, 0.098 milligrams per kilogram. For groundwater, the models would predict an action level of 190 micrograms per liter. This isn't just strictly the action levels, it's also the models we use have been calibrated to field data. So we're very confident of especially our groundwater screening levels, that if the concentration of PCE in groundwater is less than 190 micrograms per liter, you're unlikely to see PCE in soil vapors, I think within 10 feet of the groundwater, greater than 920 micrograms per cubic meter. So And the soil action levels, we discussed this in our guidance document for vapor intrusion. Really, I wouldn't put much stock in them. They're not very, there's a lot of uncertainty in predicting from models the equilibrium partitioning of, say, PCE from soil into a vapor phase. You're better off just go straight out and get soil gas models. That's what the vapor intrusion models for soil do. Step one is partition, input a concentration, it partitions and estimates the concentration in soil gas. So you just get soil gas, soil vapor data directly instead of relying on the soil action levels if you think there's a VOC contaminated soil at a site. So typically in vapor intrusion, step one is to get soil and groundwater data. Step two, if there's a reason based on a suspect source, then you get soil gas data. You could get deep data close to the source, but especially you want to get shallow data immediately under the slab of the building. And I think in the next slide we talk about moving toward large volume purge samples instead of these tiny 1 liter soil gas samples under a slab building we've been doing in the past. Step three is collect indoor air data if there's a reason to. But you always want to identify a source and have it documented before you go to indoor air. We'll talk about that in a minute. So there are our screening levels then for PCE, for vapor intrusion. We see we're starting to fill in this graph for screening levels for individual environmental hazards. So you see the action levels for, we already had one for indoor air, so now we have an action level for vapors being emitted to indoor air from soil, also for soil gas, and for PCE and groundwater vapor intrusion action levels. Step three, indoor air sampling, and there's a lot of debate about this, and I definitely don't agree with what's being done on the mainland, where there were some problems with the models in the past, and they didn't really understand heterogeneity of vapor plumes, which I'll mention here, I think, in the next slide. So there was a conclusion where the models are wrong. So we can't use action levels for groundwater or for soil vapor to predict potential impacts to indoor air. Just go straight to indoor air, where the models aren't wrong. I mean, physics is physics. What was wrong was the way that the samples were being collected. They were relying on discrete vapor samples in particular. We were testing a random 1 liter sample of vapor, say under this house, and then using it to predict impacts to indoor air. Well, in the past, the thought was that the vapor plumes were very uniform under the slab of building. So you only need to collect a small sample, whatever the lab needed, and then you can estimate vapor attenuation based on a single sample in the slab of building and an indoor air sample inside the building. Well, that didn't work at all. So the conclusion was by some parties where the models don't work. Like I said, it's not the models, it's the sampling. So indoor air sampling, you always want to identify a source first and then go to indoor air. Or if you have to do it concurrently, make sure you get soil vapor data and ideally groundwater data if it's shallow. And again, as we discussed in a separate webinar, our office is definitely moving toward collecting really large sub-slab vapor samples. Or the sample itself is small, but it represents thousands of liters of air instead of random 1 liter sample. That's a separate webinar. One thing I pointed out is the sub-slab attenuation factors. They vary with respect to the climate. So Hawaii's vapor intrusion action levels are not going to be adequately conservative for colder climates. In areas of the U.S. or any part of the world where a building is heated, they're at a much higher risk of vapor intrusion because heating a building tends to depressurize it, and you have a much higher risk of vapors being pulled up through the floor of the building. Also, in colder areas, the buildings tend to be less well aerated. They don't get as much fresh air averaged over the year as in more moderate climates, and definitely not in places like Hawaii, where I like to say I haven't closed my windows for my apartment in about 15 years. So in this is the paper we published, again, with Josh Nagashima and I, Mark Rigby, excellent risk assessor we've been working with for years. Mort Smith, Harry O'Neill are their top-notch vapor intrusion and soil vapor sampling consultants on the mainland. Really, they work internationally. We published a paper in 2014 where we looked at building engineer designs and the building HVAC system design, energy designs and such, and other issues, indoor air exchange rates in different climates. And we published a paper, Estimation of Generic Subslab Attenuations for Vapor Intrusion Investigations in Different Climate Regions of the U.S. or anywhere in the world. So the higher the number that you see here, the SSAF, subslab attenuation factor, the less attenuation because it's inverse. So in Hawaii, we assume attenuation factor of 0.0005 or 2,000-fold attenuation, whereas in a colder area, of the U.S., this VIR, Vapor Intrusion Risk Region A, across the Midwest and Northeast, and then Alaska. The attenuation factor assumed there, again based on building data, these aren't just models, 0.003, or about a 300-fold attenuation. So it's not that far apart, but in general there's about a 6-fold factor of greater risk for vapor intrusion in colder parts of the U.S. than there are in tropical areas. And the areas in between, the factor is a little bit smaller, but still significant. So the main point there, don't use our action levels for vapor intrusion in cold areas. They need to be adjusted. Another point we make in our vapor intrusion webinars and papers we published, in 2012 the USEPA published what they referred to as an empirical database, where they used it to develop indoor air subslab attenuation factors. Again, the problem, as I mentioned before, is they were collecting a single 1-liter sample under a building and a single indoor air sample, comparing the data and saying, well, here's our attenuation factor. Well, the numbers were all over the place, and you can see that in the graph that summarized their data here. And this would only be valid if the vapor plume under a building was uniform, so you can collect a sample from anywhere, you're going to get the same attenuation factor. Well, now we know since then that vapor plumes under buildings tend to be highly heterogeneous. So you collect a soil vapor sample in one part of a building, a 1-liter sample, move over 20 feet or to another part of the building, collect a sample. It could be orders of magnitude different. There have been some attempts to fix this, to try to fix this database just through statistical analysis where you can't do that. If the individual data points are unreliable, unverifiable, then you're done. This wasn't a bad science project. I looked at this database for years myself. It was originally developed around 2001, but it was a dead end in science. And science has a lot of dead ends, and that's what we do. We learn from the dead ends and we move on. So attempts to call this the 95% UCL, they developed this database of 0.03, which is at least an order of magnitude to 2 orders of magnitude lower than it needs to be. The assumption was that vapors are only attenuated by a factor of 30 as they intrude a building. It's completely wrong. There's no basis to that. And saying that it's more conservative, so we're going to use it. It would only be conservative if the approach used to develop that method was scientifically valid. But it's not scientifically valid, so it's not conservative. So just to rant about that a bit. This has been going on for several years, but some agencies are still clinging to this 95% UCL. From a science standpoint, maybe it doesn't seem like that big a deal, but using this causes the action levels or screening levels for vapor intrusion to be excessively conservative, and it draws in thousands or tens of thousands of property owners and business into this hypothetical vapor intrusion risk that causes them a lot of financial and legal problems, and ultimately probably leading to a lot of brownfields. Anyway, we have webinars posted on this to our webpage, so check those out for more details. Okay, that was vapor intrusion. Next, let's look at soil leaching action levels. You see the equation we use up here in the upper right is the concentration in soil, the action level is equal to your target concentration in groundwater times some constant 6,207 times that chemical's Henry's constant plus 0.166 times that Henry's sorption coefficient, KOC. This was actually a simple algorithm derived from a model referred to as seasoil. It was actually a pretty complex leaching model developed, I think, by the Department of Agriculture in the 1980s, and then modified for use for environmental contamination. It's a lot of trouble to run the model. We ran a lot of these in the 1990s. I was in a team working with Oak Ridge National Laboratory to try to simplify it. Washington, I think it was Oregon State actually, someone there, Mike Anderson, 1991, ran hundreds of models and came up with this simplified algorithm based on default really conservative scenario that groundwater is 5 feet below the base of the contaminated soil, and a few other like minor mixing in groundwater. So now, based on this, from a leaching standpoint, if you're looking at leaching from a forward model, first you look at the concentration of contaminated in soil, and then the model would predict the concentration in the source leachate, that dissolved phase fraction that's leaving the contaminated soil migrating downward, say with rainfall. And then step 3, the model predicts the concentration of contaminated leachate at the groundwater interface. You could be losing some of the mass in the leachate if it's a volatile chemical from volatilization out of the leachate as the leachate migrates downward. The model does not include biodegradation, but that could be included in some models. But the concentration might be a little bit different at the groundwater interface. And then step 4 of the model is just mixing of the leachate with the groundwater that's slowly migrating beneath this contaminated soil as the leachate rains down into it and creates a groundwater plume. Well, to calculate the leaching action levels, we just do this in reverse. We take this algorithm developed by Mike Anderson in Oregon, plug in your target groundwater concentration, you plug in the chemical's Henry's constant, absorption coefficient, and it about calculates the soil action level for leaching concerns. So back to our example PCE environmental action levels. So residential site scenario, or unrestricted land use as we refer to it, exposed soils over a source of drinking water. So in this case again, it doesn't show here, but the target action level we were using for groundwater is the MCL 5 micrograms per liter, because it was the lowest of all the action levels for groundwater for PCE under this scenario. So we plug that into the model and we back calculate and get a soil leaching based action level of 0.64 milligrams per kilogram. Now we know from field experience that the sea soil model we use over-predicts contaminant desorption from soil and concentration in the leachate as it's migrating downwards. And this is just because, again, the problems of all these models predicting desorption of a contaminant from the soil into leachate or desorption of a contaminant if it's volatile and into vapor phase. The models tend to way over-predict how much of the contaminant is going to migrate or move into leachate, soil moisture, or into the vapors. Just because the factor that's used to look at sorption, this sorption coefficient, was developed from laboratory studies that looked at actual sorption of the chemical to organic carbon. They didn't look at desorption of the chemical. And as one person who does this described it to me, it's kind of like Velcro. I'd say a ping pong ball covered with Velcro. It's a lot easier to stick to another piece of Velcro, take less energy required to stick it to that piece of Velcro than to desorb or pull that ping pong ball off of the Velcro. So desorption coefficients, if we actually had them, which we don't, would be much higher than the sorption coefficients, which would mean that the actual concentration of the chemical migrating to leachate would be much more than predicted by the model. So we know this, so the leaching based action levels are way too conservative, by, at least in order of magnitude. So what we have guidance on to address this issue is laboratory-based leaching tests referred to as the synthetic precipitation leaching procedures, SPLP. Some of you might recognize the term TCLP, toxicity characteristic leaching procedure. Same type of test. They're both batch tests, as they're referred to. These can be used to much more accurately estimate the KD factors, the sorption coefficients, and leaching hazards. We have separate guidance on this and even a spreadsheet where you input the total concentration of the chemical in soil, input the concentration of the chemical that was reported for the SPLP batch test, and it'll calculate a sorption coefficient for you, and also a more realistic concentration of the chemical in leachate. I won't go into it in detail. That's posted to our webpage. The test is pretty simple. You take 100 grams of soil, and this should be soil collected from a multi-increment sample, not discrete samples. You want to make sure that the laboratory processes that sample very carefully and selects this 100 grams of soil from multiple points, 30 or more points within the sample that you sent them. But it's just essentially several spoonfuls of soil mixed with 2 liters of fake rainwater. And then you agitate it for 18 hours or something like that. And then you look at the mass of the chemical that moved into the rainwater, into the solution, and compare that to the mass that remains sorbed to the soil, and that's your sorption coefficient. Now even this model isn't that great. It doesn't exactly mimic what's happening in the field. So in the future we're probably going to move toward the LEAF. I forget what this acronym stands for, but it's a leaching type laboratory model where it's based on soil column tests. So you take your soil as undisturbed as possible, put it in a column, and then you trickle water through it. Again, same type of solution probably as using the SPLP test. And look what actually leaches out of the soil and calculate sorption coefficients and such. That's a It's already out there, but we haven't incorporated it into our guidance yet. It's mostly used for pesticides. And the SPLP leaching procedure in Hawaii, it's been used a lot for organochlorine pesticides when they get flagged for potential leaching concerns. The SPLP batch test almost always show, in fact, the chordane and deodorant and such aren't that leachable from soil, even though the models predict it and the action levels predict it. You can also use it for metals. Same issue with metals. They tend to be not very mobile. That was leaching-based action levels. The groundwater to surface water action levels, again, a big issue in Hawaii, and it's a big issue when I worked in San Francisco for California EPA. Just discharges of plumes of petroleum-contaminated groundwater and solvent-contaminated groundwater into the shoreline areas of San Francisco Bay or into streams. That was a big issue. And early on, there was an idea with this groundwater is, okay, we know it's moving. We accept that, and discharging it. Actually, I take that back. They didn't know it was moving. There was an assumption that it was stagnant. And it's not a source of drinking water along the shoreline. So a lot of the groundwater was determined not to be an issue no matter how contaminated it was. There was no need to remediate the groundwater. But we soon realized, especially when we started mapping out these solvent plumes, some of them were a mile long, that the groundwater is migrating. And it is slowly discharging into the bay. And if you go out at low tide, I'll show you some pictures in a minute, then you can actually see springs of fresh groundwater discharging along the shorelines. So in this photograph here, you see the red staining in the back. This is actually from a creek near San Francisco. The red staining is caused by iron and other metals in groundwater that's discharging from a spring here. So it quickly oxidizes as soon as it hits fresh air, leaving the stain. So if you're ever hiking along streams, just look for red stains, and they identify springs of groundwater discharging. So in this case, the aquatic toxicity action levels have to be met at the point that the groundwater is discharging into the surface water body. So in this case, this stream was actually an important trout. I think it was a trout habitat. So discharge the contaminated groundwater into small pools like this can create what one eco-risk person called basically toxic plumes or dams, a toxic dam that prevents fish from migrating through this area. So that's the point of our groundwater surface water action levels, is to protect aquatic toxicity. It doesn't take into account mixing and dilution, and it shouldn't, because it's here in the next slide, the benthic organisms and sediments don't get the benefit of dilution. This was discharged to freshwater springs along shorelines on the Big Island in Hawaii. I actually tasted some of this water. It's perfectly fresh. The Hawaiians knew this also. So they would take jars out and collect fresh water while they're hanging out at the beach or along the shorelines. They'd have to go inland to get fresh water. But again, the benthic organisms in the sediment here, they don't get the benefit of any dilution and mixing of groundwater as it migrates up and mixes with the fresh water. And of course, the groundwater is going to get diluted in the contaminant concentrations pretty quickly away from the spring areas, but not right at the spring areas, and definitely not in the sediment. So our action levels, at least to a screening level, don't take into account this dilution and mixing. It can be looked at on a site-specific basis. So there are action levels in for discharge the groundwater in aquatic habitats. The chronic action level for PCE, aquatic toxicity, 53 micrograms per liter. So fish could be exposed to this, or benthic organisms, whatever, for long periods of time without health effects. The acute toxicity or immediate health effects for PCE in aquatic environments, the published action level is 1800 micrograms per liter. These might be Hawaii specific, acute and chronic promulgated standards. And for terrestrial habitats, again, we don't have action levels for ecotoxicity. That's more of a site-specific call. Lastly, gross contamination action levels. We've done a lot of work on this in Hawaii, especially, and again, when I worked in San Francisco Bay Area, because there was a lot of shallow petroleum contamination in areas that were being redeveloped. These caused huge problems for developers. In this particular case, the photograph here is a classic example. I use this in a lot of my presentations. That's me in the far background up on the concrete wall looking down at this. This is a gas station that was excavated out to 15 feet or so back in the 1990s. And there's no free product on the groundwater. There's another 30 feet or so of this gravelly soil. And they did a risk assessment. They only looked at benzene, I think even in soil gas and in soil, and it passed the risk assessment. There wasn't much benzene at the site. It was probably a low benzene gasoline release to start with. We also discussed in our paper on the chemistry and toxicity of petroleum vapors, why vapor plumes for petroleum tend to get depleted in the aromatics like benzene pretty quickly. We see that in the field all the time. Anyway, at this site, past a risk assessment, our office was overseeing installation of a underground parking garage, and the soil caught on fire. So how can this soil catch on fire and pass a risk assessment? Well, it's because at the time we didn't look at TPH. If we'd taken soil vapor samples here, we would have seen really high levels of TPH gasoline, even though again benzene BTEX probably weren't a problem. And they were in this case they were at flammable levels. This isn't methane, it's gasoline. You could smell it. So gross contamination refers to instances like this where you could have short-term vapor emission problems posed by workers at the site, or at a site in Honolulu several years ago. They were digging up a diesel tank, and yes, as we discussed in our field study paper on TPH vapor chemistry, diesel fuel is vapor, is volatile. That was a big debate. It still is, I guess, to some extent, but I always like to say go to a gas station and take the nozzle off of the diesel tank and take a deep breath, and then let me know if you think it's diesel fuel isn't volatile or not. In the case in Honolulu, diesel tanks were being removed from a site. It was a slightly windy day, and the vapors from diesel coming out of the pit were so high they went across the street and got sucked into the HVAC system of a state building across the street. They had to evacuate the entire building. This is what we mean by short-term vapor emission concerns. Also explosive vapors, as you're showing here. Again, every time they drug the backhoe through the soil, here it would set off a spark. There were a lot of quartz pebbles, and it would catch the vapors on fire. Thus the consultants out there in their Tyvek suits with the fire extinguisher. They had to go in and eventually get a remote control backhoe. You notice here there's no operator to finish excavating the site. Potentially mobile free product on soil can cause a lot of problems for groundwater discharges into storm drains or something during dewatering. Or if you're digging up the soil and stockpiling and it rains, you get sheens coming off your stockpiles and running down the street and causing problems in the storm drains and such. Staining or just visible debris, like we mentioned before, lots of bits of chromium or something at a site. The gross contamination action levels are intended to identify all these problems and avoid any interference with future development. So if it can't be cleaned up, you map it, show where this contamination is, describe what the potential problems are, and then a real simple environmental hazard management plan on how to manage this soil and groundwater if the site is redeveloped. Because you don't want to find out these problems as you're developing the site. It can cause, again, huge problems and shut down $100 million projects. So if the risk assessors don't want to know, then because it's gross contamination, not direct exposures, you should still put it in your reports as a consultant, just if nothing else from a liability standpoint, so you're warning future developers or users of the property. Anyway, that's gross contamination. So here's the gross contaminations for PCE. So according to Massachusetts, some of the guidance they publish where they look at odor thresholds, volatility and other issues, you can start smelling PCE in soil around 170 milligrams per kilogram. So if you're at a dry cleaner site and thinking, wow, this soil stinks of PCE, you got several hundred ppm PCB in the soil most likely. Groundwater, you can start to taste PCE in groundwater according to some studies done in the past. They're published. You start tasting PCE in groundwater just coincidentally at 170 micrograms per liter. In this case, this is an issue because the taste threshold for PCE in groundwater is higher, much higher than the drinking water toxicity action level. So you can be drinking water contaminated with PCE well above the toxicity-based threshold and not know it because you can't taste it or smell it. The opposite is true for a lot of petroleum chemicals. For gasoline and diesel, it's pretty close. So you can start to taste gasoline or diesel in water at about the same time it hits a toxicity threshold. For something like xylenes, which have very low toxicity, I think the drinking water standard for xylenes is 10,000 micrograms per liter, but you can start tasting it at 50 ppm. So if you had a groundwater, it's a source of drinking water contaminated with xylenes, you'd have to clean it up to address gross contamination concerns more than you would toxicity concerns. So that's gross contamination. That's just a quick review of all the action levels. And ultimately, after you've done a good job characterizing the site using DU-MIS methods, now you screen the site data using these action levels. Then you'll write a report. The report should cover the the site background, give a summary of the investigations, how samples were collected and such. Then compare the site data to the action levels or screening levels if you're using the tropical Pacific version. And then you prepare the environmental hazard evaluation. You identify potential hazards at the site. You do an advanced evaluation of targeted hazards if necessary. So maybe you run SPLP leaching test on the soil to see if the chlorine is really leachable. Or you collect soil vapor samples under a building and maybe even indoor air, but after soil data or groundwater data, some of the reasons suggest there could be a significant source of volatiles, chemicals in the building. You could also look at even direct exposure hazards, maybe modify the exposure scenarios. Is it 200 milligrams a day a kid eats or 100 milligrams a day? That's more traditional risk assessment. Then you would end with conclusions, recommendations, summarize your findings, recommend any additional site investigation needed, additional data collection, any advanced evaluation of targeted or identified hazards. And then you might recommend to go ahead and prepare a remedial action plan or prepare a long-term environmental hazard management plan, or no further actions required. This is all components in an EHE report. More commonly, the EHE is just included as a separate section of a site investigation report where you discuss comparing the site data to action levels, identifying potential problems, then any advanced evaluation and subsequent conclusions regarding hazards at the site. So the more complex sites tend to require a separate EHE report. It's just a quick summary of environmental hazard management plans. This is also discussed in our technical guidance manual. It's really pretty simple, common sense, especially for simple sites. Long-term management contaminant, residual contamination, same information that would be in EHE. Very typically these are prepared as separate documents or at least an attachment to a site investigation report. And one thing in here, you always want to include 2-scale maps of the affected areas, no more sketch maps hand-drawn that say not to scale. Again, the future property owners need to know exactly where this contaminated soil or groundwater is so they can manage it properly in the future. As part of the HME, you give a real short summary of any potential environmental hazards identified associated with the soil, and then a short summary of the restrictions for site use or management needs, so soil and groundwater management, the need for caps, vapor barrier systems, etc. Land use restrictions, if maybe the site should only be used for commercial industrial use without any further evaluation or controls. And also, very critically now, you have the CHMP. It's important that you consider it in the budget for future development and maintenance at a site. So this would, again, be usually 2-step. You have your initial EHMP. The site's going to be redeveloped. You prepare a construction EHMP that very specifically describes how to manage soil and groundwater at the site. The site's redeveloped. Its contamination is left in place after redevelopment. Then you prepare a post-construction EHMP. And again, start over just by updating your EHE. I'm going to finish the webinar with a quick discussion of risk. And again, looking at the direct exposure action levels based on toxicity. Earlier in the webinar, I demonstrated using very simplified equations how the basic equation of risk equals your average daily dose times the toxicity factor can be rearranged to calculate toxicity-based direct exposure action levels for any type of media, whether it's water, soil, air. At the bottom here, the media action level is equal to the target maximum average daily dose divided by the exposure rate, or the exposure to that media on a day-to-day basis. Well, a key component of this target maximum average daily dose is the target risk that you want to protect the receptor against. So for cancer risk, most of us are familiar with the concept of 1 in a million cancer risk, or 1 in 100,000, or 1 in 10,000 cancer risk. It's something very similar for non-cancer risk, or just impacts to kidney function and such. It's called the non-cancer hazard. So these numerical risks play an important role in the action level models. Again, these models, these equations are linear. If you increase the target risk by a factor of 10, then you're also going to increase your action level by a factor of 10. So the action level is very dependent on the target risk, and it's important to understand how we develop these target risks and how we apply them to the action level models. Let's look at risk versus remediation. So what target risk should sites be remediated to? Here's a quote from USEPA 2017. So removal management levels. These are alternative screening levels used for remediation purposes. So where the cumulative carcinogenic site risk is less than 10 to the minus 4, or 1 in 10,000, and the cumulative non-carcinogenic index is less than 1, action is generally not warranted. So what this is saying is that action is only warranted, or cleanup is only warranted, when your cancer risk at the site exceeds 1 in 10,000, not 1 in a million. This was a misconception I had definitely in my earlier days, that the sites should always be cleaned up to meet a 1 in a million risk. Well, that's not the case. Here, sites need to be cleaned up under EPA's guidance to meet 1 in 10,000 risk. That's the cumulative risk posed by all the contaminants at the sites together. They should be remediated to meet a cumulative non-cancer index, or non-cancer hazard index, of no greater than 1. So you can see the graph at the bottom here. I've modified this from this actual document I referenced above. To the right is a higher risk, to the left is lower risk. So higher risk, the 10 to the minus 4, once you exceed the 1 in 10,000 cancer risk, or contamination at the site exceeds a 1.0 non-cancer hazard index, remediation measures are warranted. If contamination at the site poses less than a 1 in a million risk, or 10 to the minus 6, or it poses less than non-cancer hazard of 0.1 or 0.2, then no further investigation is even warranted at the site. It's a low risk. Anytime you're within this range in the middle here, you mainly want to ensure that your cumulative risk limits are not exceeded. You want to make sure your site investigation is done very well. Your data are reliable, again using DU-MIS methods. And you want to have high confidence that you're not exceeding these maximum risk limits. Now, if you do exceed these maximum risk limits, and other considerations can also be taken into place. It doesn't mean the site has to be cleaned up to meet 10 to the minus 4th risk, all the contaminated soil treated or removed. Sometimes that's just not feasible. So in this same guidance discusses other considerations, including remedial feasibility, exposure to scenario, your target contaminants potential concern, your confidence in toxicity factors. All these elements can be taken into consideration both when setting your final cleanup target risk and also in developing action levels, because action levels again are based on some target risk, but it doesn't always have to be 1 in a million. Just some other quotes from earlier EPA guidance documents. US EPA 1991, this was an Oswald directive. For sites where the cumulative site risk to an individual based on reasonable maximum exposure, these are the exposure assumptions we still use in US EPA's regional screening levels and our direct exposure action levels, is below 10 to the minus 4th. In other words, it's a low excess cancer risk. Action generally is not warranted at the site. US EPA 1994 National Contingency Plan, in cases which result in a cumulative risk in excess of 10 to the minus 4th, or otherwise high excess cancer risk, site-specific factors may be considered when determining your final remediation concerns and such. In both cases, these also references target risk with respect to the need for remediation of 10 to the minus 4th, not 1 in a million or 10 to the minus 6. So what do we mean cumulative risk, and how does this compare to your target environmental action level risk, or the risk used to develop these our direct exposure action levels? Cumulative risk you can think of in the same ways as we think of calories. Let's say your target maximum calorie intake in one day or per day is 2,000. That maybe you have a piece of cake and a cookie and a drink, and the calories in each one of these is far less than 2,000, so it's not a problem, right? Well, no, cumulative risk just means you have to add up the calories for each one of these things that you're ingesting or being exposed to a day. So in terms of contaminant risk, cumulative risk equals the risk posed by chemical A plus the risk posed by chemical B plus the risk posed by chemical C, and so on. So you add all these together, and that's our cumulative risk. So just like our diet, food, individual chemicals might not pose a risk, but in combination, the risk could add up. In combination, it could pose potentially significant risk. So the target risk for individual chemicals that you see listed in our action levels, and even in the US EPA Region 9 regional screening levels. We'll look at those in a minute. The target risk for individual chemicals is typically set lower than the maximum acceptable risk. So for example, the excess cancer risk of 10 to the minus 4 with a hazard quotient of 1. Additional consideration of cumulative risk is required if the number of chemicals with similar health effects present at the site exceeds the number exposed or the number assumed in the action levels target risk. This is rare if you set your action levels properly. The goal is not to have to go back and calculate cumulative risk and add additional time and cost to the project. So we include a table in our Appendix 1 of the guidance, Table J, that summarizes, just in general for general knowledge, target health effects by individual chemicals. This is really getting into the realm of risk assessors where you do need their expertise when you start looking at cumulative risk on a site-by-site basis. So this is an example of a PCE target risk versus the selection of the direct soil direct exposure action level in a residential scenario. So on the left we have cancer-based screening levels. On the right we have the range of potential non-cancer based screening levels for PCE and soil. So from a cancer risk standpoint, again, the maximum target risk we would ever want to use for a chemical to develop an action level is 10 to the minus 4th, this remediation goal, which in the case of PCE in residential soil equates to a concentration of 110 milligrams per kilogram. Now we wouldn't want to set an action level, especially for PCE, at this concentration. You have to think of other considerations. For one thing, PCE is a volatile chemical. From a risk standpoint, inhalation is especially high risk you want to pay attention to. It's also high confidence in the cancer studies used for PCE. We actually use toxicity factors published by the state of California, which are an update to the ones published by USEPA. And also PCE is very typically present with other carcinogenic volatile organic compounds, TC and such. So in the case of PCE, the target risk of 10 to the minus 6 or 1 in a million, the equivalent soil action level in this case is 1.1 milligrams per kilogram. If we want to use a target risk of 10 to the minus 5 or 1 in 100,000, our soil action level for residential soils would be 11 milligrams per kilogram. So we have this range of action levels to pick from that falls within this range used to develop action levels and screening levels, the target risk range, somewhere between 1.1 milligrams per kilogram and 110 milligrams per kilogram for PC and soil cancer risk. Let's look at the non-cancer hazard quotient, or soil action levels associated with non-cancer risk. So in this case, the maximum that we would ever want to use is for a non-cancer hazard quotient of 1. In this case, for PC and residential soil, this equates to a concentration of 87 milligrams per kilogram. So we're already lower than the maximum allowable action level for cancer risk, 10 to the minus 4 at 110. At a target hazard quotient of 0.1, it would be 1/10 of this. So our action level would be 8.7 milligrams per kilogram. Now what this means is you could have up to 10 other chemicals in the soil at their action level if it's based on 0.1 hazard quotient. And if you had 10 other chemicals at their action levels, the risk would still just add up to 1, or hazard index of 1. So you're safe using that. That's pretty conservative. In most cases, it's very rare to see more than 2 or 3 or 4, definitely no more than 5 chemicals at a site that pose the same health effects. So what we do as a default in Hawaii is we use a default non-cancer hazard quotient of 0.2 to develop our action level. So in this case, the action level is 17 milligrams per kilogram. So there's our choice. For non-cancer risk soil action level, we would use 17 milligrams per kilogram as a default. But for PC and soil, just because it's a volatile chemical, we're really concerned about inhalation, there's a lot of confidence in the cancer studies, then we use a very conservative, the most conservative action level of, based on a 1 in a million risk, 10 to the minus 6 of 1.1. So if you look in lookup tables, it's in the Appendix 1 for the residential soil action levels, you'll see this action level for PC and soil of 1.1. And that's what it's based on. We didn't have to do that. In reality, that's excessively conservative. There would have to be 100 chemicals, carcinogenic chemicals, at their action levels to add up to an excess cancer risk of 10 to the minus fourth. But that's what we have as our action level for these reasons given below. That's PCE. Let's look at arsenic. So first, again, the cancer-based action levels, the range that we could use on the left, and then the range of potential non-cancer action-based action levels for arsenic in soil on the right. Again, a residential scenario. So for cancer concerns, a 10 to the minus fourth risk, the maximum where something would definitely need to be done in a site. The equivalent action level for arsenic in soil residential scenario is 41 milligrams per kilogram. At a 1 in a million risk, the action level is just 100 times, or 100-fold lower than this, 0.41 milligrams per kilogram. 10 to the minus 5 risk, 1 in 100,000, 4.1 milligrams per kilogram. So there's our range of potential action levels from a cancer standpoint for arsenic, 0.41 to 41 milligrams per kilogram. Now, I meant to mention before for PCE, the USEPA regional screening levels, by default for their cancer-based action levels or screening levels, they only put action level associated with 1 in a million risk. It's the most conservative you would ever need to use at any site, and that's what they use. And they use this with an understanding that this is where you start. It doesn't mean that's the cleanup level. It means here's where you start if you exceed this action level, or if you're developing alternative action levels. Then you take into account other considerations based more site-specific. What's the natural background? Or say for PC, what's your toxicologist's confidence in the cancer-based studies? Maybe it's less and they're okay with a higher, less conservative target risk. But EPA always publishes the most conservative screening levels for carcinogens. So that's the range for cancer risk posed by arsenic in soil. How about non-cancer hazard? In this case, based on a hazard quotient of 1, the soil action level for arsenic in soil would be 23 milligrams per kilogram. So this is the maximum concentration of arsenic in soil that would equate to what is considered the non-threat threshold, or the no observed effects threshold for arsenic in soil. Again, it's not a black and white line. It just means that the toxicologists agree that this dose equivalent, or this concentration in soil, wouldn't pose a risk for long-term exposure to the soil. Let's look at a hazard quotient of 0.1. So is 1/10 of this, at 2.3 milligrams per kilogram. We could set the action level to this, 0.1, and just use an action level of 2.3 milligrams per kilogram for arsenic in soil. Well, we start to run the same problem we have using the 10 to the minus 6 cancer-based action level, 0.41 milligrams per kilogram. Naturally occurring arsenic in soil across most of the world is above 0.41 milligrams per kilogram. So that's really a useless screening level, useless action level. And again, I know the people who publish the US EPA regional screening levels, they know this. And that they're not saying to use this as a screening level. They're just saying, hey, start with this. Don't worry about any action levels or screening levels below this number. Now start taking into account these other considerations. So we do this. So for arsenic especially, we look at natural background, which in Hawaii, total arsenic natural background is, we use that action level of 24 milligrams per kilogram. We also looked at the toxicity studies for arsenic in a lot more detail. The cancer-based toxicity studies, especially when you start trying to predict down to 1 in a million risk or 1 in 100,000 risk, really is very low confidence in those studies. A lot of guessing and projections that probably aren't valid based on field observations or epidemiological studies. So we look at we have much higher risk in the non-cancer studies. So just by default, we're going to start looking at the action levels based on non-cancer risk more than we are at excess cancer risk. Also, when arsenic is present in soil at sites in Hawaii, usually associated with pesticides, often with sugarcane use or use around buildings or other equipment for weed control, arsenic is almost always the primary risk driver. So from a cumulative risk standpoint, if any other carcinogens were present, they're only a minor contribution to risk. You can essentially ignore them. Also in Hawaii, we don't look at total arsenic in the soil. We based all our regulatory decisions on bioaccessible arsenic. Arsenic in soil tends to bind very tightly to iron or other hydroxides in the soil and not be bioaccessible, which means if you swallowed the soil, then 99% of it, or 95% or something, of the arsenic would go straight through you. It's not going to get stripped from the soil. So we have special tests in our guidance on how to test the soil for bioaccessible arsenic. It's very similar to an SPLP batch test. You just put a couple of spoonfuls of dirt in 2 liters of fake stomach acid or gastric fluid and agitate it for 10 or 20 hours and look at the amount of arsenic that gets stripped from the soil and moves into the solution. This is the bioaccessible fraction of arsenic. So taking into account all these factors, these really Hawaii specific, but in general specific considerations that would apply to a lot of other places, then we opted to select for our action levels, in this case, to use the least conservative but still protective action level for arsenic in soil based on a hazard quotient of 1 of 23 milligrams per kilogram. So if you look in our guidance or in our EALs and the lookup tables for residential land use or in the EAL Surfer, then that's the number that'll come up for arsenic in soil, 23 milligrams per kilogram. It's based on a not conservative, the least conservative we'd ever want to back off to for hazard quotient of 1, and then also on the other factors. And again, you would test the soil for bioaccessible arsenic if the total arsenic exceeds 24 ppm. So that just gives you an idea of how the action levels for direct exposure are developed. And we're not wedded at all to this target risk of 1 in a million risk, or even a target hazard quotient of 0.2 or 0.1. These are just recommendations, or they're just guidance published by USEPA as a starting point. But the states are under no obligation to use these or to base cleanup on a 1 in a million cancer risk. That's always a state-specific prerogative, at least in the U.S. The USEPA has delegated most of the responsibility for cleaning up contaminated sites in the U.S. to the individual state agencies. They're assigned this responsibility, and then the USEPA provides technical support. I'd say up front that the USEPA's regional screening levels, they're initially published in the early 1990s. I've been talking to some other people in USEPA who oversee this, and just publishing these screening levels and getting away from having to do a site-specific risk assessment that would take a year, where you look at site data and calculate risk, it saved private enterprises in the U.S., private property owners, billions of dollars. You think of the hundreds of thousands of sites that have been investigated, the cost just to do even a simple risk assessment, at least 5,000, more complex ones, 50,000 or more. So it's one of the most beneficial things the US EPA has done for the individual states, critical part of technical support they provide. So as I said, we're not wed to this target 1 in a million risk or even the 0.2 hazard quotient. This is as conservative as we ever need to go when we're designating these or developing these action levels used in Hawaii. We use this as a default. We use an excess cancer risk of 1 in a million as a default start and a hazard quotient of 0.2. So for the excess cancer risks, the screening levels we publish for direct exposure are 100 times below the level that might be acceptable in a site-specific risk assessment. And that for non-cancer risks, hazard quotient 0.2, the screening levels there are 5 times lower than what might be acceptable in a site-specific risk assessment if those were the only chemicals present. We use this as a default for most of the volatile chemicals for the same reason. The vapor toxicity studies tend to have a high level of confidence, and we're also much more aware, more concerned about exposure via inhalation. That's a very obvious exposure route, whereas exposure to soil is probably overblown in a lot of cases. People aren't as exposed to as much soil as we predict they are. But we can start to back off from there. We start looking at compounds like ethylbenzene, naphthalene, heptachlor, heptachlor epoxide, and looking at the toxicity studies from a cancer standpoint. We have much higher confidence in the non-toxicity studies than the non-toxicity factors. So in these cases, we back off to an exposure cancer risk of 10 to the minus 5. So we're 10 times higher than what we would be at a 1 in a million cancer risk when we're developing cancer-based action levels for these chemicals. Then to develop the non-cancer-based action levels, we still stick with that conservative hazard quotient of 0.2. And then we develop action levels for each one of these concerns, cancer, non-cancer, and we take the lowest one. That becomes the final direct exposure action level. For PAHs, it's a big issue. It's one of the first issues I worked on as a risk assessor. I was working in New England and Massachusetts at the time. They were doing the Big Dig, if anyone knows about it, a huge tunnel they dug. So they didn't really find much in the soil except benzoate pyrene in these pHs. At the time, they were trying to screen them out to 1 in a million cancer risks, which equates to action levels well below 1 ppm. And anywhere they tested, they found it. Pretty soon they realized that the pHs in the soil there was widespread contamination of soil, very low levels, but most of it was caused by auto exhaust. So as the auto exhaust goes up in the air, it's got pHs in it, and then it rains back down. When it rains, it brings it back down to earth and contaminates the soil to trace levels of pHs. And you'll find this in any urban area. Anthropogenic background is equal to action levels, at least based on excess cancer risk of 10 to the minus 5. So if you're trying to screen on 1 in a million cancer risks, you'll get lost in background. So for the carcinogenic pHs, we back off again to a target excess cancer risk of 1 in 100,000 to develop more usable action levels. In the case of benzoate pyrene, EPA just published some documents on non-cancer based studies, which have a much higher level of confidence than we do in the cancer-based studies for benzoate pyrene. So we focus on that. We even back off further for the target exposure excess cancer risks for benzoate pyrene. We use it 5 times 10 to the minus 5. So we're almost up to that 10 to the minus 4 maximum target risk. But still, the action levels we develop, I think our action level for residential is 3.6 ppm. Yeah, it's very useful. It's still adequate safety margin. Usually if pHs are present, benzene is the sole risk driver. And also it's above anthropogenic background in urban areas, not only from auto exhaust but also from asphalt. We have this discussion in our guidance. Anytime you're near a road or around any old roads where the asphalt's crumbling, you're going to find benzoate pyrene and other pHs at low ppm level. You'll know it's from the asphalt because the TPH will be very low, even though the benzene is up to say at 1 or 2 ppm. This is because all the petroleum is heavy in from asphalt. It's not going to show up in TPHG or TPHD or even TPH residual oils. Massachusetts, after their Big Dig study and looking at toxicity factors and such and anthropogenic background, they set their benzoate pyrene action level or screening level at 2 ppm, so essentially the same as ours, 3.6, to help rapidly screen out anthropogenic background, get these sites characterized that are contaminated, if they are contaminated, and deal with the remediation without getting lost in background. So that's the pHs for chlorinated PCBs. Similar, focus on non-cancer risk or higher confidence in those studies. We back off again to a 10 to the minus 5 excess cancer risk, still an order of magnitude safety margin before we hit that 10 to the minus 4 maximum limit. In this case, when we see these chemicals at sites, they're always the primary risk driver, or almost 99.9% of the time. So in this case, we're comfortable backing off to a hazard quotient of 1, also from a non-cancer standpoint. So we can set the non-cancer action level to the maximum allowable with a hazard quotient of 1. This again makes these action levels a lot more usable. It spares us from having to do unnecessary risk assessments, which would only ultimately conclude that your hazard quotient is less than 1 if we'd set our action level at 0.2, or if we'd use a 10 to the minus 6 cancer risk. The risk assessment would conclude, well, your risk is less than 10 to the minus 5, so you're done. It's really a waste of time. We can do that up front in the action levels. And again, all these things I'm going through, this is one of the key problems once we got site investigation down. The key problems that create a lot of brownfields is using excessively conservative action levels and screening levels, and that we know we could clear up front, and that would pass in a site-specific risk assessment. So all this has a lot of experience built in. So you see the other action levels here. I won't go through them in detail. Aldrin, Dealdrin, same thing. We back way off on excess cancer risk as a really low confidence in the cancer studies, focus on non-cancer risk. Has a quotient of 0.5 because they usually co-occur with nothing else. Arsenic, TEQ dioxins, hexavalent chromium, again, much higher confidence in the non-cancer studies, so we back off as far as we can on the excess cancer risk, 10 to the minus 4th. They're almost always the primary risk driver to site. So we also back off to a hazard quotient of 1. This is as far as we can back off to develop screening levels. So the screening levels you see in our guidance for arsenic, TEQ dioxins, hexavalent chromium, they're as high as you're going to get. There's really no use in doing a site-specific risk assessment. and attempting to use an alternative target risk to develop site-specific screening levels. These also take into account natural background at sites. So those, you don't need to do a site-specific risk assessment. This is pretty much what you get. If you exceed the action levels, some type of remediation is going to be warranted, either to limit exposure or to clean up the site. TPH, again, the main risk for TPH is non-cancer. For TPH, or for petroleum, for cancer concerns, you focus on the aromatics that have very detailed cancer studies like benzene and even ethylbenzene, even naphthalene. For TPH in general, we focus on non-cancer risks. You test the aromatics, evaluate those separately, at least the few shortlist target. And again, TPH, from a non-cancer standpoint, the bulk TPH is always going to drive non-cancer risk, non-cancer hazard over individual chemicals, so we can back off to a hazard quotient of 1. Last one, lead's a totally separate model. I won't go into details. We reference the model in our guidance. Hawaii reduced their target residential screening level for lead from EPA's 400 ppm down to 200 ppm 10 years ago, knowing back then that they're eventually going to drop their lead screening level, their action level, down to below 400. Now, I've heard and seen some documents suggesting they're going to drop it all the way down to 80 or 75 or something, below 100 ppm. Well, this is going to be well below anthropogenic background in urban areas. And again, just like PAHs in Boston during the Big Dig, if you're trying to screen sites using an action level for lead really below 200 ppm, our action level, then you're going to get lost in background pretty quickly. So for a lot of these chemicals, we set the target action levels a little bit higher than they would be with the most stringent risk. But when you find contamination, we encourage people to clean up to background, say for lead, 75 ppm, if it's feasible at a site. Same thing for arsenic or dioxins. Sometimes it's feasible, sometimes it's not. But that's also discussed in our guidance. Tap water, you see a note down at the bottom, is the default MCLs promulgated by USEPA and state agencies are almost always based on a target excess cancer risk 10 to the minus 5. If it's not an MCL promulgated, we use EPA's tap water action levels. They're based on a target excess cancer risk of 1 in a million, 10 to the minus 6. So they're very conservative in that respect, but then they're based on a hazard quotient of 1, which is the maximum, the least conservative. So that's kind of odd. You'd think they would base the tap water action levels also on a conservative hazard quotient of, say, 0.1 or something. So that's a quick review of modifications we use, or kind of agency-specific considerations we use in setting target risk to develop action levels. And I want to really highlight, we spend a lot of time thinking about these individual chemicals over many, many years, looking at toxicity studies, looking at feasibility in the field, anthropogenic background, natural background. So it's not something you can just change quickly. And just because EPA's action level for arsenic or dioxins or lead or anything or lower than ours doesn't mean, well, it's more conservative, so we should be using EPA's action levels. Well, or regional screening levels. Not the case at all. We're not required at all to use those. And if you talk to people that develop them, again, that the whole point was they're going to set them much lower than is probably needed, and then the states can use their own decision, their own expertise to make state-specific action levels. Okay, so I got a quick comparison here. HDOH action levels versus California environmental screening levels, US EPA regional screening levels. California ESLs, I helped develop those. I worked with California EPA 1999, 2005, and I was actually hired specifically to develop screening levels for California. We'd already done it in Hawaii several years before, just to help get the majority of sites through this risk assessment process as quickly as possible and redevelop. Again, the biggest problem there, the holdup, was time. It wasn't necessarily money, but when the contamination is discovered, usually it's in the middle of a redevelopment project, and they don't have time to spend a year and a half. I know one site, they spent 5 years on the risk assessment. It was actually pretty ridiculous. We could have set screening levels up front, agreed on target risk, and avoided the risk assessment. So a quick comparison here. So Hawaii's action levels, you see all the X beside the soil and groundwater target environmental hazards. Of course, we address all these. If you're familiar with California's ESLs, they address the exact same environmental hazards, not a surprise. We coordinate updates for our guidance. and make sure we're roughly doing the same thing. US EPA regional screening levels, they only address toxicity. They only address direct exposure for soil. They don't address vapor intrusion, leaching, gross contamination, any other concerns you might have. They have to be addressed separately. Same thing for groundwater. The tap water RSLs published by EPA, again, they're just screening levels. They're not promulgated standards, required use. They only address drinking water toxicity. They don't address vapor intrusion, discharge to aquatic habitats, gross contamination, anything else. So a key thing here is the US EPA RSLs can't be used as standalone criteria to screen a site because they're not comprehensive. You're missing all these other potential issues. Just because you pass a direct exposure action level for soil or meet a drinking water toxicity MCL or tap water screening level for groundwater doesn't mean there's no problems at the site. You still could have vapor problems or impacts to aquatic habitats or gross contamination problems. Another difference with California ESLs for vapor intrusion, again, we discussed before, the ESLs in California reflect a colder climate than we do here in Hawaii. So they assume that buildings are heated for part of the year, not as much as say they are in the Midwest and New York. So there's less fresh air flowing through buildings. They're heated part of the year, so you have a higher rate of vapor entry during the cold weather months. So the California ESLs, I think they're about 2 to 4 times lower than Hawaii's ESLs, are more conservative because there's a less attenuation of vapors as they mix into indoor air. So the vapors under the building need to be at a lower concentration to avoid impacts to indoor air. And your groundwater screening levels also be lower. How about target risk? And we already talked about this extensively, so I won't get into it too much. Again, in Hawaii, for our EALs, we spend a lot of time looking at chemical specific, the most optimal excess cancer risk. And we select from a range of 10 to the minus 4, 10 to the minus 6, depending on that specific chemical or family of chemicals. Non-cancer hazard quotient, again, our default is 0.2, but for some of our chemicals, we're comfortable backing off to the maximum non-cancer hazard quotient of 1. So your action level will be 5 times higher than it would be at 0.2. California ESLs, this is we use an excess cancer risk of 1 in a million. If I could go back, I would definitely adjust those. And I work with the people there all the time, so they're familiar with our guidance. And maybe slowly over time, they'll back off on some of their action levels based on cancer risk. Again, just to get through this process faster, so you don't automatically throw someone in to do a risk assessment and spend a year on that when we could have cleared the site with less conservative but still rational screening levels up front. For California ESLs, they use a non-cancer hazard quotient of 1. Even though they use the most conservative action level for carcinogenic risk, they use the least conservative action level for non-cancer risk. This was really a problem after I left. We initially had set our action levels in California ESLs to a non-cancer hazard quotient of 0.2. Reasonably conservative, takes into account cumulative risk. Someone made the decision to change it to 1 because that's what the US EPA RSLs used at the time. It has a quotient the least conservative of 1. The problem with this is now with California ESLs, the ones that are based on non-cancer risk of 1, that means that you have to calculate cumulative non-cancer hazard at every site where those action levels are used, or else you're not adequately addressing potential cumulative risk. Well, nobody does that. In reality, you have your site data, you have these screening levels, ESLs. If they're below, then you assume you're done. And most regulators don't understand this caveat in the California ESLs. Hopefully they'll change that. US EPA used to do the same thing, and that was the problem in this switch they made around 10 years ago. In the past, US EPA regional screening levels, again, based on the most conservative excess cancer risk, 10 to the minus 6. I mean, in reality, it's just too conservative for almost everything. But then in the past, they were using the least conservative non-cancer hazard quotient of 1. So you get really high screening levels for soil for non-cancer risk, that you could have potential cumulative risk problems at a site if there are multiple contaminants present with the same health effects. Well, a few years ago, US EPA people that do the RSLs, and again, we talk all the time, they added a separate section of RSLs based on a non-cancer hazard quotient of 0.1. So 1/10 of the maximum that you could use. So this is a really useful thing to do. We use 0.2, they use 0.1. It's fine. But if you use 0.1, RSLs based on 0.1 hazard quotient, you don't really need to worry about cumulative risk. The excess cancer risk, they use the most conservative 10 to the minus 6. What I like to see them do is publish a separate set of screening levels based on a target excess cancer risk of 10 to the minus 4, the maximum. So then EPA would be publishing a range of action levels or screening levels for cancer risk and non-cancer risk that then the states or consultants could take into consideration on a site-by-site basis. So that's some issues there. I think Hawaii is kind of ahead of the game in this report, this standpoint, like we are in soil sampling, because in Hawaii we can't afford to have brownfields. This is a lot of people know I'm working with the Chinese Academy of Sciences. They have the same issue in China. Is there's not that much land that's usable, and what is usable you grow crops on or people live on. So they can't afford, like we did in the mainland US, to simply walk away from a site because the discrete sample data were causing you to get lost and there's no endpoint to the site investigation, or the screening levels being used were way below what they needed to be, and cleanup costs were going to be excessively high. This again was the cause of a lot of brownfields on the mainland. In Hawaii, we don't have the opportunity, the luxury of being able to walk away from a piece of land and abandoning it as a brownfield and going somewhere else. So we have to be a lot more careful in the way we do site characterizations and the way we develop action levels. It's more efficient. We can get in and get out. That's the same approach I'm working on with the Chinese Academy of Sciences. They can avoid some of these problems that we've had for 30 years, especially still now in the U.S. mainland. They're moving along in the mainland. They just don't have the same sense of urgency that we have in Hawaii to do this, or that the Chinese government is having in China. Little background history. The last thing I want to go over is the Hawaii issue, again related to risk assessment and 95% UCLs. So this is again a holdover from the days of discrete soil sampling, where from a risk assessment standpoint you always wanted to use a 95% UCL of the data, or a very conservative estimate of the mean concentration of the contaminant in the soil based on this sample set of discrete sample data that you were given, and probably didn't have a chance to go out and collect more additional samples to confirm. Now, from an MI standpoint, when using multi-increment sampling approaches, you only need to calculate a 95% UCL and apply that to your data if the replicate multi-increment sample data relative standard deviation exceeds 50%. This is getting really rare. This is discussed in section 4 of our TGM. I'm not going to go into detail for it. Now, for discrete sample data, the 95% UCL was applied to discrete sample data in an attempt to address distributional heterogeneity, or variability between sample data. For multi-increment sample data, as we discussed in one of the webinars, I think webinar number 3 for our DUMIS webinar series, under MI sampling approaches, we use sampling theory to address variability. It's been used in mining and farming for years, decades. Under sampling theory, to address variability, you collect a really big sample, and there's a equation you use to calculate the actual mass of sample you need to collect based on concentration, particle size, and such. For soil, if you're looking at ppm level contaminants, you need to collect at least 1 to 2 kilograms of soil. That's in our guidance. You also use sampling theory in the laboratory. So the laboratory doesn't just take a random pinch of dirt off the top of a jar like we used to do in discrete samples. I certainly did that many times. First 10 years of my career. The laboratory has to spread out now. Take this large multi-increment sample, dry it, sieve it, spread it out, and then subsample it very carefully from at least 30 to 50 points or more, same as in the field, and test a minimum of 10 grams. That's calculated again based on particle size when you sieve it to less than 2 millimeters. And then that's what they test. So sampling theory is used to address variability in MI sample. Discrete sample data, the field representative of a single data set, for one thing, is unknown, as we showed in our study, and we see all the time in multi-increment samples, replicate data, if the samples weren't collected adequately, the mean concentration you can get from testing a single set of points within an area, a given area, can vary by orders of magnitude, and definitely by a factor of 2 or 3, even in the most uniform type contamination. So for discrete sample data sets, the field representative of a single data set's unknown. You go back to the same site, collect the same number of samples from different points, you can get a completely different mean. Also, sampling theory for particulate matter is not considered. There's no consideration of minimum mass required under sampling theory, which is statistically based, or processing of the samples in the laboratory. Outlier data are also tossed from discrete sample data sets because you're not getting the RSD that you want. You're trying to force the data to match some distribution. This has always been a big problem, especially for the field people who know they collected that sample. They know that part of the yard has high PCB, so deleting or ignoring outlier data in risk assessments was always ridiculous. And then so this is why in the past the 95% UCL was applied to discrete sample data. A lot of the risk assessors were aware of one or more of these problems. They knew there was a lot of uncertainty in data, so you want to be extra conservative to it. So we don't need to do that anymore with multi-increment samples because sampling theory is taking care of that. Only when your RSD for your replicates is getting high, we start to get a little bit worried about how representative the data are. But even then, we're still much more confident than what we would know from a single set of discrete sample data. So the last question I'll end up here with is that this also often comes up. Well, don't I need to look for acute hotspots within a DU with discrete samples? That's the reason I should collect discrete samples. Let's look at that issue. And again, we discussed this in webinar number 3 in our DU MIS series. So how do I assess acute risk? So let's say there's a hypothetical regulatory requirement. This is actually real. I won't name the state. And it was reasonable to think of. There's nothing wrong with it. It's the hypothetical requirement was that no single discrete sample in the upper 3 inches of soil in a residential yard shall exceed 400 milligrams per kilogram lead due to short-term risks. So they're assuming if a kid ate a pinch of soil that had more than 400 ppm lead, there could be immediate health effects. In reality, there's a lot of problems with that from a toxicity standpoint. EPA, among others, published some guidance just suggesting you need to be exposed over at least a 90-day period before your blood levels would be elevated to a level that would pose permanent long-time damage. That's a separate issue. Let's just stick with this and say it's a one-time exposure. So let's think about this in more detail now. We'll just accept what the toxicologists are telling us. How would we demonstrate this in the field? Let's assume we have a 20-foot by 20-foot front yard, and we're looking at the top 3 inches of soil. Switching to the metric system, this is a total mass of soil about 3,000 kilograms. So our goal as a geologist now, or as a field person, is to demonstrate that in this 3,000 kilograms of soil, there's no single discrete sample that could be collected that would exceed 400 milligrams per kilogram lead. So the first question now from a field standpoint is, I'm asking the risk assessor, my other half of my personality, what soil mass does this 400 milligrams per kilogram apply to? Or in sampling theory, what is my decision unit? So from a discrete soil sample is typically 100 grams. That's about a handful of random dirt thrown into 4-ounce jars. In this case, the front yard is 3,000 kilograms. That's 30,000 potential DUs. So you, risk assessor, are telling me, the geologist or the field person, I need to demonstrate to you that no single one of those 30,100 gram masses of soil in the front yard exceeds 400 milligrams per kilogram lead. Well, how would I do that? No, if you mean 100% confidence, I would have to test every 100 gram mass, 30,000 samples. Well, that's probably not going to happen. Let's think about it in more detail. When in reality, you're collecting discrete samples, the lab's just taking a random pinch of dirt out of that jar, even if they try to homogenize it. Like we said before, all the fines will probably go down to the bottom where most of the lead is. Let's just assume it's the standard lab subsample mass for metals is 1 gram, which is it's below any level that you'd allow under sampling theory, any mass. The minimum mass under sampling theory for less than 2 millimeter particles is 10 grams. So there's a problem right there. Let's ignore that problem. So how many 1 gram mass DUs do we have at the site? Well, now we have 3 million potential DUs that I'm supposed to demonstrate to the risk assessor that no single 1 gram mass exceeds 400 milligrams per kilogram lead. Well, that's a problem. I could use some statistical methods, maybe test 59 of those 3 million potential DUs. And if I do that, then I can supposedly conclude that 95% of the DUs I didn't test don't exceed 400 ppm of the maximum concentration of lead that I identified in the soil. Still not a 100% confidence level. Or I'd be 95%. The 95% of the DUs I didn't test don't exceed the maximum level identified in the soil. Is that good enough? I wouldn't be very confident with that. I'm testing 59 1 gram masses out of 3 million. Well, what does 1 gram mass have to do with risk assessment anyway? Well, nothing. From risk assessment standpoint, the risk assessors are asking this. I should be looking at 200 milligram masses. That's the default child ingestion rate that we're currently using. Well, now I have 15 million potential 200 milligram masses of soil in that front yard. So how many of those do I need to test to demonstrate that no single 200 milligram mass of soil exceeds 4 million or 400 milligrams per kilogram? Well, you can see this is getting pretty absurd. Well, in a reality standpoint, we're talking about acute risk. So a risk assessor will say, well, we're going to focus on pica children. These are children that tend to eat everything in front of them, including dirt. The default soil ingestion rate for pica children is 10 grams. It's roughly a small spoonful of dirt. So that's a little more reasonable, a little more. Now it's risk-based. You're telling me something to test in the field, risk-based. Demonstrate that a pica child wandering across this front yard isn't going to instantly ingest 10 grams of soil that exceeds 400 milligrams per kilogram lead. Well, I still have 300,000 potential Ds in the front yard. So you can see how this is going. Well, in reality, it can't be done. In reality, acute soil screening levels, for one thing, and acute toxicity factors for most of the chemicals aren't even available. So there are no screening levels to do this. And even the lead screening level, 400 ppm, would be highly debatable. Other risk assessors I know would say it should be thousands of ppm, even tens of thousands of ppm. So there are no screening levels to begin with for most contaminants. And the next is it's not feasible to negate the presence of small masses of theoretically acutely toxic soil with any degree of confidence based on either discrete or MI soil sample data. You're never going to do it. I'm never going to provide that level of confidence. So in reality, if you think maybe you have lead paint chips in the front yard or little bits of lead shot, say in this front yard, if you want to address risk, forget sampling. You need to scrape the site and get rid of it, or cap the site. That's the only way you're ever going to address acute risk. And then once you do this, then you evaluate chronic risk, and you want to use multi-increment samples again, much higher reliability. Collect triplicates, 50 increment samples in this front yard. You'll have very high confidence of what the true concentration of lead is in that front yard, of the mean concentration. And you can assume that if you're addressing chronic risk at the site, then you're also going to address theoretical acute risk at the site. That's generally reasonable, and that's really the best you can do. So that's it. Just in summary then, we talked about how environmental hazard evaluation is a way to expedite the risk assessment process, the traditional Superfund process, and get you through that second stage of a site characterization or site investigation process much more quickly than in the past, so you can get in, identify problems, and remediate a site. Key point: use of reasonably conservative our environmental action levels or screening levels expedites this risk assessment and remediation process, so you don't unnecessarily throw a site into a risk assessment phase when you could easily clear the site just with reasonable screening levels or action levels up front. Again, you want to ensure that you include comprehensive action levels. They address all potential environmental hazards at a site. That's one reason that I get really nervous when I see a risk assessment, because I know it's focusing on direct exposure. They're probably not even thinking about leaching concerns. Big issue in Hawaii, the next nearest source of fresh water is 2,000 or 3,000 miles. Vapor intrusion concern, gross contamination concerns. So it's really important. It's really useful in our action levels we developed over the last 20 years now. They comprehensively address all these common concerns. In some cases, we might be concerned about plant uptake and such. We've had some sites, arsenic contaminated sites like this. Forget action levels at that point. Go out and test the soil. Do an MI sample across the garden for the soil. Do it in triplicate so you know what's in the garden, and then do an MI sample of the produce in the garden, and you can look at uptake of contaminants in the soil. In this case, it was arsenic into the produce. Again, you don't want to use discrete samples for either the soil or the produce, because it's going to be highly variable and you're not addressing the main point. You'll never be able to get down to that resolution of uptake in the single eggplant of arsenic from the roots. And the cumulative risks that we used in commonly accepted adjustments for target risks are incorporated. They're built into our action levels and our EHE guidance. But we also provide guidance on advanced site-specific evaluation for identified potential environmental hazards as necessary. A lot of times this isn't it's just not useful. It's no cost benefit to looking at, say, direct exposure or even a lot of risk in general on a site-specific basis. For vapor intrusion, you almost always want to go out and get soil vapor data. That's the advanced site-specific evaluation, but you don't need to run individual site-specific vapor intrusion models. We already have that covered. Then the results recommendations included in the EHE report, or the EHE report, and included in the site investigation report. And then if any contamination left on site, you summarize the EHEMP, and that's used to develop long-term management for contaminated soil and groundwater during future redevelopment and such. So that's it. Thanks a lot for joining us, and we look forward to any recommendations that you have for additional update to our guidance. Again, back to the Confucius reflection, imitation, and bitter experience. Really, our guidance it's not something we develop blindly in our cubicle. It's really a collection or a compilation of our collective experience in Hawaii and other places I've worked over the last 25 years now. So it's nothing I came up with. I just take notes from all the experts in the field and our experiences. Thanks.